Unit Overview. This unit provides an introduction to data structures. The fundamental concepts and principles presented here are applicable to the main themes covered in the subsequent units. The unit begins with an overview of data types. It then discusses the distinguishing features of data structures and their organization. Finally, the concept of abstract data type is introduced. It is also explained how abstract data types promote the principles of software engineering and object-oriented programming. Objectives. After completing this unit, you should be able to understand the concept of data structure, distinguish between data structures and data types, learn how data structures are organized in computer, describe the characteristics of common types of data structure, understand the concept of abstract data type, describe the advantages of abstract data type. In computer science, data structure is a study of various ways of organizing data in a computer so that it can be used efficiently. Invariably, the information contained in a data structure is manipulated by a systematic and step-by-step process which is called algorithm. The manipulation of data structure may involve such operations as adding an item, searching for a particular item, deleting an item, rearranging data items in different ways. Thus, data structures and algorithms are closely linked together and play a complementary role in many applications. Over the years, data structures have gained significant importance because of their usage in several disciplines. Data structures are an integral part of modern operating systems, compilers, database management systems, data communication, and system software. Likewise, algorithm together with associated data structures have widespread use in several applications, including image processing, digital signal processing, simulations, numerical computations, cryptography, data compressions, and genetic studies. In this introductory unit, we shall introduce basic terminologies and concepts concerning data structures. Data types. All programming languages provide some built-in data types which are useful for efficient coding of programs. The predefined data elements are separated into two classes which are known as primitive and composite. A primitive data type defines a set of values and operations that can be performed on these values. The familiar primitive data types are integers, real numbers, characters, and Boolean, which are supported by almost all programming languages. A Boolean type can have only two values, true or false. The basic operations on these values are AND, OR, and NOT. An integer type can assume different set of values depending on implementation in a particular language. The set of basic permissible operations on an integer type are, for example, arithmetic operations and comparisons operations. The primitive data types are also called atomic or irreducible because these cannot be expressed in any other basic types. The primitive data types are always supported by the underlying hardware features and to a lesser extent by the compiler systems. This means that the range of values and the allowed operations depend primarily on the hardware circuitry. In general, the number of bits allocated to each type decides the range of values. For example, an integer type is often implemented using a 32-bit storage representation with 1 bit reserved for sign. In this way, the integer type can have a range of values over a billion. Characters are implemented by using 8-bit for ASCII and ABCDIC representation and 16 bits for Unicode. The later representation allows a range of values over 65,000 for encoding characters. The operations on primitive data types are often included in CPU instruction set. When such support is lacking, the compiler depends on built-in software routines. A notable example is the implementation of floating point operations. On small computers which do not have floating point circuitry, the real numbers are manipulated using software instructions. Of course, this approach considerably reduces the computational speed, often by a factor of 100 to 1000. Different programming languages provide a variety of primitive data types, which are identified by language-specific keywords. For example, Java defines 8 primitives. An important feature of Java primitives is that each data type is made up of a fixed number of bits, which is independent of a particular implementation. For example, an int type always consists of 32 bits and character of 16 bits on all platforms. C provides an assortment of primitive data types which are identified by the syntax int, float, character, double. The numeric type may be further qualified as short or long, signed or unsigned. C does not support Boolean data type. Instead, numeric 0 and non-zero values are interpreted as false or true. Further, the size of C data type varies with platform dependent. Visual Basic provides support for all basic types identified by the keywords integer, long, single, double, byte, and Boolean. The primitive types can be created as local or global, with each type preceded with the word public or dim. Composite data types are larger and more complex data types which are defined using combinations of primitive types. The common examples of composite types are arrays, vectors, and strings. An array is a collection of homogeneous data types. Almost all programming languages support arrays as built-in data types. We shall explain the detailed properties and uses of arrays in a subsequent unit. Vectors are essentially a mathematical representation of arrays. They differ from ordinary arrays in their implementation. For example, Java provides vectors as an array of flexible size. Strings are combinations of characters. The support for strings as a built-in data type varies a great deal with the programming languages. If string is defined as a primitive data type, string data is stored in an array of characters with a special delimiter. This is the approach followed by C, C++, Ada, and Pascal. In C, for instance, a string is represented as an array of characters with the null character in the last position. Fortran 90 and Visual Basic provide support for strings as primitive data type with associated operations of assignment, join, comparison, and substring references. In Java, strings are supported as built-in type of string class. Data structure. The built-in data types provided by programming languages are adequate for solving simple problems. In fact, all computer applications in early days depended exclusively on the built-in elements of the host programming languages for the storing and processing of different data types. This was particularly true of numerical or scientific-oriented problems. With the dramatic increase in the use of computers in various disciplines, it was realized that the primitive data types were not sufficient or powerful enough to solve advanced problems involving complex structural relationship among data items. The need for new data types was further exacerbated by the recent paradigm of object-oriented approach to problem solving. Data structures are meant to serve these needs. Simply stated, a data structure is a programming construct that stores a collection of data items. At first sight, data structures might appear as an extension of composite data type. This is true in a limited sense. Actually, there are two subtle differences. First, the term data structure encompasses composite data type defined in a programming language. It may even be a user-defined type to serve a particular application need. Second, and more importantly, a data structure implies some kind of organization or relationship among the constituent data items. For example, a character string, whether defined as an array of character or treated as primitive type, has a definite order of organized characters. An alteration in the order changes the memory and characteristics of the original string. On the basis of structural relationship, the data structures are classified into two types, linear and non-linear. A data structure which organizes data elements in a sequence, that is, one after the other, is referred to as linear. Array is a common example of linear data structure that exhibit linearity. Other examples are linked list, stack, and queue. We shall dwell at length on these data structures in later units. Here we briefly introduce these types. A linked list consists of data items called nodes. Each item contains an information field and a link field pointing to another data item. A stack is a data structure which works on the principle that last item added to the collection becomes the first item that can be taken off, like a pile of trays. It is also called LIFO, last in, first out data structure. A queue is a data structure in which an item can be added at one end and an existing item in the collection can be removed from the other end. It works on the principle FIFO, first in, first out. In a non-linear data structures, the relationship between the elements is more complex. It can be, for example, hierarchical, that is, one element may be linked to more than one element in the collection. Further, the linkage may be single or bidirectional. The nonlinear types are also referred to graph data structure. Common examples of nonlinear data structures are trees and graphs. A tree is a data structure consisting of a set of data items called nodes which contain an information field and linkage to one or more data items in a hierarchical order. There are several variations of trees. Some useful types are referred to as binary trees, AVL trees, red and black trees, splash trees, B trees, and heaps. We shall study their properties in a later unit. A graph is a set of data items called vertices or nodes connected by links, edges, or arcs. Operations on data structures. It should now be clear that data structure provides a logical relationship among the elements in a collection of data items. To be able to use these elements, it should be possible to apply some kind of operations to the data. First of all, we should have some mechanism to create a data structure and reserve storage in the computer to hold the data items. Also, once the data structure is not needed, it should be possible to remove the data items and release the allocated storage. Thus, creation and deletion are the two fundamental operations associated with any data structure. Other operations depend on the nature of data collection. Generally, the common useful operations include inserting, sorting, searching, merging, and traversing. Inserting involves adding a data item in a specified position to the data structures. Sorting consists of arranging the data items in specified order. Searching means finding a given data item in the data collection. Merging involves combining two sets of data item belonging to the same structure into a single set of items according to some defined criteria. Traversing means accessing each element of a data structure at least once. This operation is particularly useful on trees and graphs. It is also referred to as visiting. Undoubtedly, the strength of a particular data structure is determined, among other things, by the nature and variety of operations that can be performed on the data elements. User-defined data structures. The data structures stacks, queues, and trees described earlier are general-purpose data types. These are sometimes referred to as classic data structures. Because of their frequent use, some of the programming languages, such as Java, provide built-in support for these structures. However, we can also invent our own data structures to meet the specific need of an application. Such data types are called user-defined data structures. Suppose we want to store records of employees, each record consisting of employee's name, designation, and salary. We can define a data structure emp using cDataType struct and then create an array of employee data structure. C code for user-defined employee data structure is shown on the screen. The elements of employee data structure can be accessed using C's pointer notation. Storage structure. The data structure provides a logical view of the relationship among the data items. Storage structure describes how the data items are stored in the memory cells of a computer. In other words, the storage structure provides a physical view or map of how data elements of a particular data structures are allocated memory space. The elements of a data structure may be stored in computer memory in consecutive storage location or in disjoint locations. Each memory location is identified by a unique number which is called memory address. For example, the characters A, B, C belonging to same data structure might be stored in consecutive storage locations identified by memory addresses 1000, 1001, 1002 as shown. This arrangement enables us to access the elements rapidly. In order to retrieve the elements, we need to know the address of the first element in the data structure. The other elements can be accessed by simply moving to the consecutive memory cells. Alternatively, it is possible to store the characters A, B, C in non-contiguous storage locations. For example, A might be stored in location 2000, B in 3000, and C in 4000. However, in order to establish the relationship between A and B, we must provide information somewhere about the location of B. This information can be placed next to A. It is called pointer or link. Thus, storage location 2000 would contain character A. At location 2001, it would contain address of the character B, which is 3000. The arrangement is shown on screen. Abstract data types. An abstract data type is a relatively new concept for describing the internal organization and functionality of data structures. It is meant to combine the description of a data structure and the set of operations that can be performed on the data elements. More precisely, an abstract data type, commonly referred to as ADT, has the following characteristics. Number 1. It provides a description in terms of data types of all data elements that make up a collection. Number 2. It defines the relationship that exists between individual elements. Number 3. It groups together all the valid operations that can be performed on the data elements and parameters that can be passed. Number 4. It specifies error condition in particular operation, if any, that may be associated with the operations. Consider, for example, the data structure stack, which we defined earlier. In order to construct ADT stack, we would need to specify at least two basic operations called push and pop. Push will add an item to a stack and pop will remove it. Other auxiliary operations might be: top will return a copy of the top element without removing it from the stack. Size operation returns number of items currently stored in stack, and isEmpty returns true or false accordingly as stack contains at least one data element or contain more. The set of operations included in an abstract data structure is called an interface. It would follow that the elements of data structure can be manipulated only through the interface. Suppose in a program we want to access the elements of ADT stack. The program should send the request to the data structures via the interface. It can get the requested element through the interface. This is shown on the screen. It is emphasized that the operations and data items in an abstract data type are all hidden from the user. A program cannot modify the operations, nor can it add new operations to the data structure. It will be seen that all built-in primitive data types are in fact abstract data types. For example, primitive float represents a range of real numbers on which we can perform basic arithmetic operations. However, we cannot add any new operation such as exponentiation to the predefined float type. Also, we cannot enhance or modify the range of values allowed by the built-in primitive float in any particular language. It should be noted that abstract data types does not specify how the data structure and associated operations would be coded in a particular program. It also does not describe what storage structure should be used, that is, whether the data elements are stored in consecutive memory cell or in disjoint areas. In other words, abstract data structures do not provide the implementation details. The user can choose any of the several available options. For example, an ADT stack may be implemented using an array or a linked list. In a software module, ADT can be viewed as a layer between the application that uses ADT and a component that implements the ADT. This is shown on the screen. The interface of ADT remains the same regardless how the data structure and operations are actually performed. Some of the high-level languages such as C, C++, and Java have built-in features which can be used to implement a variety of ADTs. C has built-in struct type, which together with other user-defined functions can facilitate the implementation of an ADT. In C++, a class construct is available for the implementation of ADT. the class constructor creates a new ADT object. The operators can be implemented through public methods. In Java, an ADT can be expressed as interface, which is essentially an abstraction of associated operations provided by ADT. Advantages of ADT. The abstract data types have several advantages over the conventional data structures. They are reusable, robust, and consistent with well-established principles of object-oriented programming and software engineering. An abstract data type can be reused at several places in a program or in different programs. The reusability of an ADT simplifies the program design and reduces coding efforts. In abstract data type, the implementation of operations and data items are hidden from the user. Thus, encapsulation ensures that the data cannot be inadvertently corrupted by a program. Further, the working of various operations integrated into an abstract data type cannot be tampered by a program. Thus, an ADT ensures a robust data structure. Finally, the ADT approach is based on the software engineering concepts of coupling and cohesion. The coupling property determines how strongly two separate parts of a program module are mutually linked together, and the extent to which a change made in one part has impact on other parts. A well-designed software has a minimum coupling of program segments. An ADT promotes weak coupling because any change in the program or coding does not propagate to any of the components of an ADT. Cohesion property determines how well integrated are the components of a piece of software. Software engineering prescribes that good designs should maximize cohesion. An ADT inherently promotes maximum cohesion in that the ADT components are well integrated into a single compact structure. Unit Overview. In this unit, we turn to the topic of algorithm. The unit begins with formal definition of an algorithm. It then describes different applications of algorithm in various disciplines. It also provides details of different techniques used for the analysis of algorithms. Objectives. After completing the unit, you should be able to understand the meaning of an algorithm, describe various formal applications of algorithms, distinguish between empirical and analytical method for analyzing algorithm, understand the use of big O notation for expressing the performance of an algorithm in terms of time and space utilization, learn rules for specifying the behavior of algorithm for large data inputs. Introduction. An algorithm is a step-by-step procedure for solving a problem. This is a notion generally applicable to problems encountered in real life. A cooking recipe, for instance, might be designated as an algorithm. However, in computer sciences, algorithm has a special meaning. Formally, it is defined as a step-by-step procedure with the following characteristics. Number 1. It must have some important data to operate on it. Number 2. It must produce at least one result. Number 3. It must terminate after a finite number of steps. Algorithms have long and fascinating history. The step-by-step procedures for solving geometrical and arithmetical problems can be traced back to the ancient Greeks over 1,000 years ago. An efficient method for finding the greatest common divisor of two integers was proposed by Euclid. However, first systematic procedures for performing arithmetic were studied in 50 AD. and recorded in an Arabic textbook by the famous Persian mathematician Al-Khwarizm. The word algorithm is, in fact, derived from the name Al-Khwarizm. Algorithm. With the advent of computers in recent years, need of appropriate algorithm for solving a variety of problems has sharply arisen. Some common types of algorithm and their uses are: searching algorithms are designed to search for a given data value in a massive data collections. Sorting algorithms are commonly used in computer applications to arrange data items according to user-specified criteria. Compression algorithms are meant to reduce the size of data and program file for their efficient exchange over the networks. These are also used for compression of image, audio, and video data. Fast Fourier transform is extensively used in digital signal processing. Encoding algorithms are used for encryption of data in secure transmission and exchange of sensitive data. Geometric algorithms are useful for identification of geometric shapes. Pattern matching algorithms are meant for comparing images and shapes. Parsing algorithms are designed to identify different programming constructs by the compilers. Classification of algorithms. Depending upon the strategy for solving a particular class of problems, algorithms are classified as iterative, divide and conquer, greedy, and backtracking. In iterative algorithm, certain steps are repeated in loops until the goal is achieved. Iterative algorithms are used commonly for sorting of small sets of data. In divide and conquer algorithm, a given problem is fragmented into smaller subproblems. The subproblem is then partially solved. The algorithm is recursively used over several parts and terminated when further subdivision cannot be continued. The divide and conquer algorithms are frequently used for searching and sorting problems. The greedy algorithms work on the principle that an immediately available best solution at each step must be chosen without worrying about its effect on subsequent steps. For example, if we want to give change for 73 rupees in minimum number of currency notes, the immediate best solution would be to start with the highest denomination, that is, a 50 rupee note, then two 10 rupee notes, then 2 rupee note, and finally 1 rupee note. The greedy algorithms are useful for solving scheduling and graph theory problems. In backtrack algorithm, all possible options are examined by moving back and forth until the solution is found. These kinds of algorithms are useful in graph theory. Two common approaches are depth first search (DFS) and breadth search first (BSF) algorithms. Specification of algorithm. As we mentioned earlier, algorithms play a central role in manipulation of data structures used in any program. In order to code the underlying procedures, it is sometimes useful to describe the algorithm in human-readable form using either natural language or pseudocode. Use of natural language. In natural language, we can use words and phrases to describe the procedure and computational steps. For example, words like read, write, compute, set may work for input, output, computations, and assigning values to a variable. Likewise, arithmetical operations can be expressed using words like add, subtract, divide, and multiply. The word repeat may be employed to express loop structure. For example, The Euclid's algorithm for finding the common divisor of two positive integers can be expressed in natural languages as shown. The algorithm is used on the observation that common divisor of two integers is also the common divisor of the difference. Use of pseudocode. The description of an algorithm in natural language tends to be wordy and verbose. Sometimes it does not clearly define and may even be ambiguous. Pseudocodes provide an alternative and better way of expressing algorithms. Pseudocodes, as the name implies, is a mixture of natural language and high-level programming notation. Although there is no standard format for writing pseudocode, the following notations are commonly used. Identification. Each algorithm is assigned a name and some identification number. Comments. Comments are optional and enclosed in square brackets. Variable names. These are expressed in capital letters. Assignment. A left arrow indicates assignment statement. Operators. Arithmetic and logical operators are identified with mathematical symbols. Input and output. The I/O operations are shown with words read and write, followed by variable names or output message. Control structure. Logical steps are expressed by using the phrase if then else. Loops. The repetitive operations are described by the word repeat, that is followed by loop structure described in terms of for or while statements. Specification of algorithm. The Euclid's algorithm for the GCD can be expressed in pseudocode as shown. The pseudocode is not only human readable, it can also be easily translated into a high-level programming code fragment. C++ code for the GCD algorithm is algorithm analysis. The performance of an algorithm is measured in terms of runtime and storage requirement as a function of input size. An algorithm that provides a correct result but takes enormously long time is not very useful. It is, for instance, of little help in real-time problems which require solution in split seconds. Likewise, an algorithm whose storage requirement increases rapidly with the input size is not amenable to implementation on small computers. Furthermore, there may be trade-off between time and space requirements. Thus, both time and space analysis is of crucial importance in judging the efficiency of an algorithm. The time analysis uses various techniques to estimate the runtime of an algorithm for a set of input values. Basically, two approaches are adopted which are classified as empirical and analytical. Empirical analysis. In empirical method, the runtime of an algorithm is measured in real time for different sets of input values. The actual time is plotted against the input size to analyze the growth rate. Figure also shows a time measurements of two algorithms for sorting. The empirical approach has several limitations. It essentially depends on the computing environment such as hardware and operating system. Thus, the result of analysis can vary with platforms. It also depends on the data set chosen for test purposes. The empirical data may not be comprehensive, covering all possibilities. To a greater extent, runtime depends on how efficient the algorithm is programmed for a particular machine. Analytical analysis. The analytical method uses mathematical techniques to estimate the runtime. The method identifies crucial operations in an algorithm that contribute significantly to the overall processing time. The number of key operations can be determined by analyzing the pseudocode for the algorithm. Let us consider the algorithm for finding the largest value in array A of size n. The pseudocode is shown in the figure. Step 1 defines a temporary variable max, which is assigned the first element A of 1 of the array. Step 2 and Step 3 compare other elements A of 2, A of 3 to A of n with max. When an element greater than max is encountered, the value of max is replaced with current element. Thus, at the end of loop, max would contain the largest array element. By inspecting the pseudocode, we draw the following conclusions. Step 1 involves one access of array element. Step 2 makes n-1 assignments to variable j. Step 3 retrieves an element n-1 times and makes n-1 comparisons. Step 4 retrieves an element n-1 times and makes at most n-1 comparisons in worst case, assuming that last element is the maximum element. Thus, total runtime for the algorithm is as shown. An important point to bear in mind is that algorithm analysis is not concerned with determining the runtime for a particular value of input. Rather, the analysis is carried out for the entire range of allowed values. Algorithm growth rates. In many cases, we would like to know how the runtime of an algorithm varies with the variation in input size. For example, we might need to know how the sorting time would grow with the increase from 1,000 to 1,000,000 items. The behavior of an algorithm, say, for very large input size is often called asymptotic analysis. In the previous example, we noted that the runtime for max algorithm varies as kn plus c, where k and c are constant, n is input size. For large values of n, the constants would become insignificant. Thus, we can say that asymptotically the runtime of max algorithm varies as n. In other words, the execution time is proportional to n. The big O notation. If the runtime of an algorithm varies in proportion to the function f of n, algorithm is said to be of order f of n. In short notation, this is expressed as O f of n. The function f of n is called growth rate function or complexity of the algorithm. Because capital O is used to express the growth rate, it is called big O notation. Thus, if runtime varies in direct proportion to n square, we say that complexity of algorithm is O of n square. Algorithm growth functions. This table shows some of functions commonly used to study the behavior of algorithms. The graph and functions commonly used in analysis of algorithms are shown on the screen. Logarithmic algorithm. The growth function has some useful properties which reflect performance characteristics of an application. The runtime of a logarithmic algorithm varies as log n, where n is size of problem. Conventionally, log has base 2. Logarithmic algorithm grows slowly and has the best performance. For example, if the problem size increases by a factor of 1,000, the runtime increases roughly by 10. Binary search algorithm has logarithmic behavior. Linear algorithm. The execution time of a linear algorithm grows in direct proportion to the size of a problem. The performance of a linear algorithm is rated as good. An algorithm based on a single loop shows linear growth rate. Examples of linear algorithms are searching, deleting, and inserting operations on arrays and vectors. N log n. The n log n has moderately high growth rate. The divide and conquer algorithms generally exhibit this behavior. Quadratic algorithm. The quadratic algorithm grows as sequence of input size. The algorithm with a pair of nested loops shows quadratic behavior. For example, the multiplication of two n by n matrices has O n square runtime. The quadratic algorithm have fast growth rate. Cubic algorithm. The runtime of a cubic algorithm varies as the cube of the problem size. Such algorithms grow very rapidly. A problem involving three nested loops has a cubic growth rate. Operations on three-dimensional arrays, for example, exhibit cubic behavior. Exponential algorithm. The algorithm with runtime of the order of 2 power n, where n is input size, are called exponential algorithm. These algorithms grow at extremely high rate and not very useful for many practical applications. Below is a comparison of growth rates of main functions used to analyze the algorithms. The Big O rules. We have seen that Big O notation provides a convenient method for expressing the asymptotic behavior of an algorithm. When the input size becomes very large, we can simplify the Big O representations using the following rules. Addition constants may be ignored. For example, obviously, constant 100 would lose its significance when n becomes very large. Lower order terms may be dropped in favor of higher order terms. For example, the simplification is based on the observation that smaller order do not contribute as much to the runtime as higher order terms. The multiplication constant may be ignored. For example, this simplification is based on the observation that in analyzing an algorithm, we are interested only in relative growth rate rather than absolute. This is shown in the graph. In-depth runtime analysis. So far, we have examined the asymptotic behavior of an algorithm. Sometimes it is useful to have an estimate of minimum, average, and maximum runtime. These possibilities are referred to as best case, average case, and worst case. Best case analysis. Best case analysis is meant to determine the minimum runtime of an algorithm. The execution time, of course, depends on the nature of input data. One or more of the inputs may result in the shortest time. For example, in a searching problem, the most favorable input would be the input value which matches the very first item in the list. In a sorting problem, the best case would be when the items in a list are already in sorted order. Best case analysis, though informative, has little practical value because in solving a problem we are often more interested in knowing the maximum time required for the solution. Worst case analysis. In worst case analysis, the maximum runtime is determined by considering the most unfavorable input. For example, in a searching problem, we determine the maximum search time by assuming that the item to be searched would occur at the end of a list. Thus, worst case analysis yields the most pessimistic time estimate. It provides the upper bound in the runtime and guarantees that in all circumstances the runtime would never exceed this limit. For such reasons, algorithm analysis is most often done on worst-case basis for most unfavorable inputs. Average case analysis. The average case analysis is done to find the average runtime of an algorithm. Quite obviously, the average time lies somewhere in between the optimistic and pessimistic time. For example, in searching problems, the average time would be the runtime when the input values lie somewhere in the middle of a list. For most problems, however, an average time can be determined by considering a distribution of input data over the entire range of admissible values. Such an analysis relies on probability theory. In general, average case analysis is more complex. Space analysis. The space analysis is concerned with determining the maximum storage requirement needed for an algorithm. The analysis, in essence, estimates the number of bytes as function of input size. Since variable and constants occupy fixed amount of storage which do not depend on the size of problem, thus space required is expressed as O of 1. The space requirement for complex data structure is estimated by counting the number of bytes for each data item. For example, an array of integer of size n would require 4n bytes, assuming that an integer requires 4 bytes. Thus, the space complexity of the array is O of n. In some cases, there may be trade-off between runtime and storage requirement. An algorithm with small runtime may require large storage space. For example, sorting of a large data file stored on secondary storage can be performed more effectively in shorter time by using a very large memory space in the main storage of a computer. Unit overview. In this unit, we explain a fundamental data structure called array. We shall examine distinguishing characteristics of arrays and look at the basic operations that are commonly performed on array data structure. The unit contains several illustrative examples to demonstrate the use of arrays. Visuals and interactive programs are also provided to reinforce the basic concepts. Objectives. After completing the unit, you should be able to learn basic concepts about array data structure, understand how arrays are stored in computer memory, know about the inserting, deleting, and traversing operations that can be performed on an array. Learn about the efficiency of basic operations. Explain the structure of multidimensional arrays and their usage. Understand the advantages and disadvantages of arrays. Introduction. An array is a collection of homogeneous, ordered, and finite set of elements. The homogeneous property implies that all of the elements of an array must be of the same type and structure. The simplest arrays normally consist of primitive data types such as integers, real numbers, characters, or Boolean values. More complex array structures might include strings and records consisting of several fields. The ordered property means that the elements of array are arranged in a sequence. Thus, each element of an array is identified by its relative position in the collection. For this reason, an array is called linear data structure. Another important characteristic of an array is the finiteness. By finite, we mean that each array can contain a fixed number of elements. In other words, an array data structure can hold specific number of elements. This number is called size or length of array. It is customary to depict arrays pictorially with elements arranged from left to right. Figure shows some typical representations of arrays comprising different data types. Observe that each array structure contains items of same type. A character array would consist solely of characters. It cannot contain integer or other types. Next figure shows examples of arrays containing composite or complex data types, namely strings and fixed-length records. Recall that a record is a collection of fields which may be of different types. Notice that in the first example, all of strings are of same length consisting of 6 characters. If there are fewer alphabets, the extra places are padded with spaces shown as Bs. The second example represents an array of employee records. In order to preserve the homogeneity property, each record should have the same size and same composition of fields. For example, the name field cannot be 20 characters long in one record and of 30 characters in another record. Likewise, the salary field must be either integer type or floating type in all of the elements. Accessing array. Each array structure is identified by a unique name. The position of each element within the array is identified by a variable called index. The range of index is referred to as index set. For example, an array consisting of 10 elements would have an index set of integers varying from 1 to 10. Sometimes the first element of array is counted as the 0th element. In this case, the index set would have range from 0 to 9. The smallest value of index is called lower bound and the largest value is called upper bound. Thus, the size of an array is given by the relation. The individual elements of an array are identified by the array name and array index. For this purpose, different notations are used. In the mathematical description of an array, the subscript notation is used. For example, the elements of array X consisting of n elements are denoted by the sequence. The programming languages, however, use bracket notation for array elements. The elements are defined by the array name followed by either parentheses or a pair of square brackets that enclose the index value. Fortran and Visual Basic use parenthesis notations such as C, C++, and Java use square bracket notation. Thus, elements of array X are denoted by. Sometimes, index is also referred to as subscript and index set as subscript variable. The contents of an array are often pictured using the name and index values. Figure shows an illustrative example of array X consisting of characters C, O, M, U, T, E, and R. Declaring array. Before an array structure is used in a program, it must be formally declared. This is required by the compiler in order to reserve necessary storage space for the array. The rules for array declaration differ with programming languages. In general, the declaration specifies array name, size, and data type. In C, C++, for example, this declaration means that the array X would consist of a maximum 100 data elements of integer type. Further, it is implicitly implied that the index set will have the range of 0 to 99. In other words, the array elements will be denoted by. In subsequent discussion, we will follow the C++ notation and rules for declaring arrays. Array storage structure. Storage structure represents the arrangement of data elements in the memory of a computer. An array is always stored in contiguous memory locations. The number of storage cells allocated to each element depends on the data types. Typically, a character occupies 1 byte, a short integer 2 bytes, and long integer 4 bytes. Figure shows the storage structure for an array mark consisting of short integers. In this storage map, the first element is stored at location 1000, second element at location 1002, and so forth. The numbers 1000, 1002 up to 1014 are referred to as storage addresses. The address of the first element is called base address. In this example, the base address of array mark is 1000. By knowing the base address, we can easily compute the addresses of other elements by using the general formula. Where address xj means storage address of the element xj, j being the index. Base address is the address of the first element x0, and size is the number of bytes allocated to an element. Thus, using the index, we can easily compute the address and access the element without the need for searching other elements in the array. For this reason, the elements of an array are said to have direct access. Further, we do not have to keep track of addresses of all array elements. Only the base address is required to process other elements in the array. It would follow that storage structure for an array is quite efficient. It has, however, the drawback that memory allocated to an array is not released until the program execution is finished. Array operations. The basic operations on an array include retrieving an element, adding a new element to array, deleting an existing element, and inserting a new element. In addition, we can perform some auxiliary operation to determine the current status of the array or obtain some information about a specific element. These operations might include the following: checking if array is full, checking if array is empty, getting index of a specified element, and traversing to process array elements. Retrieving. Retrieving an element is the most common operation. It is also called accessing. To retrieve an element, we need to know the index value. For example, mark j would access the jth element of array mark. As noted before, the computer can directly retrieve an element without examining other elements in array. Thus, accessing operation is very fast. Further, since the access is independent of the number of elements in the array, access operation has a time efficiency O1. Adding. The add operation places a new element in the array in a position specified by the index. It is also called assignment operation. Thus, if we want to move an integer n in the jth element of array mark, we simply write mark j is equal to n. If the array already contains some element in the specified position, it is replaced by the new element. The add operation has time efficiency O1. Deleting. The delete operation removes an existing element from the array. In order to delete an element, say xj, we simply move all elements after xj one position to the left. In other words, elements xj plus 1, xj plus 2, up to xn minus 1, where n is the array size, are shifted to the left. Let us consider the process of deletion of an array element. The array shown initially contains letters P, Q, R, S, and T. In order to delete Q, the element R, S, and T that follow Q are shifted one position to the left. Notice that the deletion of Q does not release any memory space occupied by the array. The elements R, S, and T are simply reorganized. Inserting. The insertion operation adds a new element to the array in a specified position without replacing any of the existing elements. The position of the elements may be specified in terms of index value or relative to an existing element. The new element might, for example, be placed before a given element. In order to insert a new element in specified location, all elements to the right of element are being moved one place to create a room for the new element. For example, if a new element is to be inserted, it is placed before an element xj, then xj, xj plus 1 up to xn minus 1, and being the array size, are moved one position to the right. Let us consider an example to demonstrate the insertion process. The array shown contains letters P, Q, R, S, T initially. In order to insert an element Z before the element R, the elements R, S, and T that occur after R are moved one position to the right. The space created due to shifting of R and other elements is filled with the new element Z. Observe that after insertion of Z, the array size increases by 1. Also note that no additional memory space is allocated to accommodate the new element. Rather, the elements are simply rearranged within the memory block initially reserved for the array. Implementation of array operations. In order to implement the basic operations on array, we define a C++ class named array, which includes add, delete, insert, and other auxiliary functions. The structure of class interfaces is shown. Add appends a new element. Delete removes an existing element. Insert adds a new element in a given position. GetIndex returns the index of a specified array element. IsEmpty checks if array is empty and returns false or true. IsFull checks if array is full and returns false or true. Disp method prints the contents of the array X. The detailed coding of all methods is given in the demonstration to follow. Array traversing. The traversal operation involves accessing and processing an array element exactly once. It is also called visiting. In order to traverse the array, we set up a loop with index varying from the lower to the upper bound. In each loop cycle, an element of array is accessed and processed according to the requirement. Some examples of traversing an array are finding the largest element, finding the smallest element, computing average of all elements, and printing contents of array. We now consider the implementation of these operations. Implementation of array traversing. A class for traversal of arrays is shown. It includes 4 methods to process an array of real numbers. Maximum determines the largest element in the array. Minimum finds the smallest element in the array. Average computes the average of all elements included. Display prints the array elements. The detailed coding of all methods is given in the demonstration. Performance of array operations. We have already seen that the time efficiency of access operation is O1. Let us examine the running time for deletion, insertion, and traversal operations. As discussed, in order to remove an element from the array, all elements to the right of the element being considered are shifted one position to the left. Thus, if the first element is deleted, there will be altogether n-1 shifts for an array of size n. Since shifting is the only major operation in deletion, we can conclude that the running time of deletion is On-1 or On in the worst case. If the last element is to be deleted, no shifting would be involved. Thus, best case has running time O1. The insertion operation is similar to the deletion operation, except that elements are shifted in the opposite direction. Thus, in worst case, the running time of insertion operation is On. To perform a traversal operation, we normally set up an iterative loop. In each loop, an element is accessed only once. Thus, altogether n accesses are made. As such, the time efficiency of traversal is On. There are no best or average cases, since all the elements need to be visited at least once. Two-dimensional array. Sometimes it is useful to group the elements of an array into smaller groups of equal size. Thus, each subgroup can be viewed as a smaller array within an array. This arrangement is referred to as two-dimensional array. For example, test scores of a group of students may be organized by student number and for each student by semester number. A two-dimensional array can be pictured as consisting of rows and columns. Figure shows such a representation for student scores by semesters. Formally, a two-dimensional array is a collection of homogeneous elements which are arranged into rows and columns. In order to identify individual elements, we need two index sets, one for the rows and other for the columns. The indexes follow the array name and are enclosed in a pair of square brackets. For example, if marks is a two-dimensional array, marks JK refers to the element is in jth row and kth column. In C, C++, the rows and columns are counted from 0. Thus, mark 00 would refer to the element in the first row and the first column. As with one-dimensional array, a two-dimensional array must be declared before it is actually processed. The declaration should specify the maximum number of rows and columns besides the array type and name. For example, in C++, the array portrayed in figure might be declared as storage structure for two-dimensional arrays. The elements in a two-dimensional array are stored in contiguous memory locations. Within the allocated memory, the elements may be stored row by row or column by column. The first arrangement is called row major and the second column major storage scheme. Figure shows a row major and column arrangements of an array consisting of 2 rows and 3 columns. If we know the address of the first element, we can compute the storage addresses of all the elements. For a row by row arrangement, the address of an element AJK consisting of n rows and m columns is given by the formula. In this formula, Base address is the storage address of the first element A00, and size is the number of bytes allocated to an array element. It is assumed that both the indexes have zero lower bounds. For column by columns arrangement, address formula is. These formulas are used by the compiler to locate and access an element of a two-dimensional array. Thus, all elements have direct access. This is the prime reason for time efficiency of multidimensional arrays compared to other types of data structures. String arrays. Two-dimensional arrays are useful in storing and processing of strings. A string is a sequence of characters which are normally stored in a one-dimensional array. In C, C++, a string includes a null as terminating character as shown in the figure. Notice that the last character in the array is null character. Thus, a string of size n is stored in a one-dimensional array of characters of size n plus 1. In several applications, such as text processing, we need to store a group of related strings. These could, for example, word in a text block or names of employees. Two-dimensional arrays provide a convenient and simple mechanism to store a set of strings. Figure shows a two-dimensional array which contains the names. This representation has the advantage that apart from having access to the strings, we can also access individual characters in each string. Since in two-dimensional array, all rows must be of the same size, we need to allocate same number of columns for all strings, irrespective of their size. Thus, unless the strings are of fixed size, some of storage space may be wasted. Operation on strings. We can perform several operations on strings that are stored in an array. Some common useful operations are inserting new strings into array, deleting an existing string, searching for a string, sorting in specified order, and listing strings. The algorithms for string operations are same as those for a one-dimensional array. However, their implementations differ. In C, C++, for example, strings cannot be assigned to variable. Instead, library functions are used for copying and comparing strings. For this purpose, the header file string.h needs to be included in the actual implementation. The interface class for string operations is shown in figure. It is designed to hold up to 20 strings, each with a maximum of 20 characters. The array is named X. It includes 3 common operations on strings. Add appends a string to the array. Del removes an existing string from the array. Insert adds a new string to array in a specified order. And disp prints the strings. Code skeleton for the basic class functions are given in the demonstration. Performance of two-dimensional array. A two-dimensional array allows direct access to any of the elements. Thus, accessing and assigning operations have a running time O1. For other operations such as inserting, deleting, and traversing, generally 2 nested loops are used. If the array consists of n rows and m columns, the loops would involve n into m cycle. Thus, the time efficiency for insert, delete, and traversal is O(n) into m. Matrix representation of arrays. A two-dimensional array of numbers is sometimes referred to as Matrix. Matrices are frequently used in computer science and engineering disciplines. In graph theory, for example, matrices are used to represent links between nodes. Image processing application stores pixel values in rows and columns for different kinds of transformations. In mathematics, matrices are frequently used to solve a set of algebraic equations. Matrices are commonly used in quantum mechanics to compute energy spectra. In engineering applications, matrices are frequently employed for structural analysis. In mathematics, the subscript notation is used for the matrix element. Further, the elements of a matrix are enclosed in a pair of large brackets. Figure shows a pictorial representation of a matrix consisting of n rows and m columns. It is called n by m matrix. A matrix with the same number of rows and columns is called square matrix. The elements of a matrix with the same subscripts are referred to as diagonal elements. Thus, A11, A22 up to ANN are the diagonal elements of an n into n matrix. A matrix is called symmetric matrix if the corresponding elements below and above the diagonal elements are identical. Thus, in a symmetric matrix, Aij is equal to Aj for all j and I. Distance between several cities, for example, can be represented as a symmetric matrix. In some applications, matrices contain only a small number of non-zero values. Such matrices are known as sparse. A special form of a sparse matrix is called tridiagonal, in which all elements above the main diagonal are zero. The elements of a tridiagonal matrix can be stored in one-dimensional array. Figure shows an example and the correspondent array. Notice that the matrix with 16 elements is stored in an array of 10 elements. It can be shown that in general an n by n tridiagonal matrix can be stored into one-dimensional array of size n-1 by 2. In this way, a large economy of storage space can be achieved. Matrix operations. Common operations on matrices are addition and multiplication. The sum of pair of matrices is obtained by adding correspondent elements. Thus, if A and B are two matrices having same number of rows and columns, their sum C is given by for all values of indexes I and j. Matrix multiplication is somewhat more involved. The product of a pair of matrices is obtained by multiplying all elements in the correspondent column of first matrix with all elements in the corresponding row of the second matrix and adding together products of elements. If C is the product of matrix A and B, the elements of C are given, assuming that both A and B are n by n matrices. In mathematical notation, the expression can be simply written as where I and j vary from m to n. The symbol sigma represents sum over the index k, which varies from 1 to n. Three-dimensional array. A three-dimensional array is a collection of homogeneous ordered data elements which are accessed using three index sets. The indexes are enclosed in three pairs of brackets which are preceded by the array name. Each index set has its lower and upper bounds. In C++, the lower bound is 0. The three-dimensional array extends the notion of grouping of elements at three levels. For example, student scores might be grouped by student numbers, semesters, and subjects. The first index would refer to the student number, second to semester number, and third to subject number. Figure shows a pictorial representation of a three-dimensional array score. Notice that the array is split into 4 tables for the convenience of pictorial representation. Inside the computer, all of the elements are stored sequentially in contiguous storage location. The elements of a three-dimensional matrix are described in terms of rows, columns, and planes. The array M of test scores consists of 4 rows, 3 columns, and 4 planes, which refer to student number, subject, and semester. For example, M 0, 2, 3 represents the score of the first student in third subject in fourth semester. Advantages of array. Major advantages associated with the array data structure are: Number 1. It is possible to use a single variable for handling a large set of homogeneous data. Number 2. Arrays provide direct access to any of the data items. Thus, storage and retrieval of information are both fast and flexible. Number 3. It is easy to construct and use arrays. Almost all programming languages support creation and initialization of array with the help of simple declarative statements. Number 4. Arrays are indispensable in implementing iterative algorithms. It is easy to set up loops by taking advantages of array index sets. Number 5. Multidimensional arrays facilitate grouping of homogeneous data items into hierarchical structure. Limitations of array. Arrays have certain limitations as well. Their main disadvantages are: Number 1. Array size cannot be increased or decreased during runtime. Thus, arrays are not useful for applications which use large data sets of unpredictable size. Number 2. Variable length strings cannot be efficiently stored into arrays because large amount of storage space will be wasted on account of padding space characters. Number 3. Insertion and deletion operations on arrays are not efficient. Every time some data item is added or removed, a large number of elements may need to be shifted. Number 4. Normally, arrays are allocated memory blocks out of the program space. For very large data sets, the program may run out of the storage space. Number 5. Some of the programming languages, such as C, C++, do not perform range check on array indexes. If an index has trespasses the upper or lower bound, incorrect data may be accessed or stored in wrong location. Some of the deficiencies of array are overcome in other data structures, which we will study in subsequent units. Unit Overview. In this unit, we will study another fundamental data structure called linked list. Like the arrays, the linked list stores a set of homogeneous data items which have linear relationship. However, linked lists have several performance advantages over the arrays, which make them more suitable for applications requiring frequent insertion and deletion of data elements. The unit begins with an introduction to the concept and architecture of a linked list and associated basic operations. A detailed formulation of algorithms for insertion, deletion, traversal, and sorting is presented. The implementation aspects of the fundamental operations are discussed in depth. The performance issues, advantages, and shortcomings and applications of the linked lists are also covered. The last part of the unit provides a description of different variants of linked list. In particular, characteristics of circular lists, doubly linked list, multilist, the relevant operations are also examined. Important algorithms for handling different kinds of lists are considered together with the programming aspects of fundamental operations. Objectives. After completing this unit, you should be able to understand the basic concepts and architecture of a linked list data structure. Learn about the storage arrangement of data elements of a list. Comprehend the algorithms for insertion, deletion, traversal, and sorting operations. Algorithms using dynamic allocation of storage space. Understand cursor implementation of linked list. Describe relative advantages and disadvantages of linked list data structure. Learn the use of linked list in different applications. Understand the concepts and structure of circular linked list, doubly linked list, and multilist. Learn about the basic operations associated with different forms of the linked list. Understand the implementation aspects of circular and doubly linked lists. Learn about the structure and advantages of multilists. Introduction to linked lists. A linked list, sometimes referred to as singly linked list, is a collection of data elements called nodes. Each node consists of two parts which are called information field and linked field. An information field contains data elements of the same type which can be primitive types such as integers, characters, or real numbers. In some applications such as database, the information pointer may contain complex data types such as records consisting of several data items. In the case, however, one data item called key value uniquely identifies each node in the list. The link field distinguishes a linked list from other data structures such as an array. The link part in a node contains a pointer to the next data element in the list. Actually, it contains the storage address of the successor node. The first data element in the list is referred to as front node or head node. A special pointer called head identifies the front node. The elements of list are normally traversed by first accessing the head pointer and then moving across the list. Sometimes a special node called sentinel is also used, which provides an entry point to the list. It can also contain other useful information about the list such as size of list, structure of a node, and so forth. If the list does not contain any data item, it is referred to as empty list. In an empty list, the head pointer is usually set to null value. The last element in a linked list is called tail node or end node. The link pointer in the tail node contains a symbolic constant null, which is meant to signal the end of the list. In C++, the null value is defined in header file string.h. Other implementations might use different constants such as -1. In pictorial representation of a linked list, cross might be used to mark the end of the list. In diagrammatical representation, The logical structure of a linked list is shown using a forward-pointing arrow to link together a pair of nodes. Figure shows a typical pictorial of linked list consisting of 5 elements. As mentioned before, a list may be used to store complex data type such as words in a text block or record in a database. Figure shows 2 such lists. The first structure contains words in dictionary order. The second list consists of student records, with each node containing roll number, name, and subject. The roll number is the key field which uniquely identifies a node. Observe that in the pictorial representation, the arrow points to a succeeding node alone. Later, we shall examine special lists in which the arrows are directed forward and backward. Storage structure of linked list. Storage structure describes the physical arrangement of nodes in computer's memory. Each node, with the exception of the terminal node, contains the memory address of the next linked node. For example, suppose that A and B are 2 nodes in a list, such that they are stored in memory locations 1000 and 2000. If B is a successor to A, then link pointer of A would contain value 2000, that is, the storage address of B. This is schematically shown in figure. Another storage structure for list consisting of records is shown in figure. The second example is particularly illustrative of how nodes of a list might be distributed in the main memory. Observe that successive nodes are not placed in contiguous storage locations. This is in contrast to the storage structure of an array, which consists of a single block of memory with successive cells allocated to array elements. In the case of a linked list, nodes might be scattered in different memory blocks. The link pointer in the nodes identifies the storage location of the successor nodes. Actually, the compiler dynamically allocates the memory space when a new node is added to a linked list. The storage space allocation is made out of a special memory block called heap. A heap is meant to provide storage space in addition to the space utilized by different elements of a program, such as constants, variables, and program statements. During execution of a program, the cells of a heap are recycled. This means that memory cells released by deleted nodes are reallocated to the newly created nodes. In this way, the linked list can be expanded dynamically. There is, however, an upper limit to heap size which depends on the computer system. In order to make efficient use of available heap space, the implementation of deletion algorithm must be designed to release the space occupied by deleted nodes. Operations on linked list. In order to access and process data contained in a linked list, we need to perform some basic operations on the list. Most applications require inserting of new data elements, deleting the existing data, printing the contents of a list, or traversing the list to access the contents of nodes. Sometimes we need to sort the list in the alphabetic or numeric order of some key data element. Searching is another important operation which looks for a given data value in the list. Other less frequently used operations include checking the size of a linked list, finding if list is empty, and copying elements of a list in another list. Normally, the operation of checking whether the list is full is not applied, because a linked list can grow dynamically by utilizing the storage space provided by heap. We now examine the implementation of these operations and explore the associated algorithms. The most common approach to implementation of linked list is called pointer method, which stores data in a collection of objects. Another method, called cursor implementation, uses arrays to store node data and linked pointers. We first discuss the pointer implementation and programming aspects of this approach. Pointer implementations of linked list. In pointer implementation, we define an object called node, which stores the data elements and physical address of the next element. In C++, structure of node can be defined using a class. Figure shows a typical class named node. Observe that the object represented by the class consists of two components. The first field is meant to hold a character string of up to 20 characters. The actual type and size can vary with application. The second field is a node pointer. It holds the address of the successor element. It is a self-referential pointer variable because it points to an object which is of the same type as the node itself, that is, of type node. The members of the class node have been declared public because other classes or their methods would need to access the data contained in node. After having specified the structure of a node, we can define an interface class for the linked list. Figure shows the basic structure of the class called linked list. It contains a private member head, which is meant to point to the first element in the list. In the constructor, it is initialized to null value. Linked list includes these public methods: add new node to the list, remove a node, print the contents of the list, sort the list, search the list, check if list is empty, return the size of the list. Actual implementation of these methods should take care of data types which may be passed as arguments and the data returned by the particular method. We shall examine these aspects when we consider the programming details of these methods. Inserting nodes into linked list. After a list object has been created, a new node can be inserted in the beginning, in the middle, or at the end of the list. Different algorithms are used to handle each of these cases. Let us explore in detail the steps involved in these algorithms. Inserting node at front of list. In order to add node at the front of a list, we create a new node and set its link pointer to point to the pre-existing first node. The front is normally identified by the head pointer. Thus, the head pointer is reset so that it points to the new node. Figure shows an example of a list consisting of 4 nodes containing letters A, B, C and D, to which a new node Z is added at the front. The end of list is marked by a cross. Next figure shows the code fragment for the method insertFront, which accepts a character string for the node value. Create a new node and adjust pointers so that the new node becomes the front pointer. Briefly, it performs these steps. First of all, a new node is created. Then, data is copied into node. Then set pointer to point to first node. Finally, readjust the head pointer. Inserting a node at end of list. In order to add a node at the tail, we use a pointer which is initially set to point to the first node. Then the list is traversed until the pointer points to the last node. A new node is created, and the link part of the tail node of original list is reset to point to new node. Figure shows the steps for inserting a tail node. Next figure shows the code fragment for the method insertEnd, which implements the procedure for inserting a tail node. It performs these steps. First of all, traverse the list. Then create a new node. Then copy data into new node. Set linked pointer to null. Finally, set pointer of tail node. Inserting node into the middle of the list. A new node can be inserted into the interior of a linked list which either precedes or succeeds a given node. The insertion algorithm is different for each of these cases. We first examine the case when new node is to be inserted after a given node. As before, we use a temporary pointer to traverse the list until the given node is reached. A new node is created, and the linked pointer of the given node is reset to point to the new node. The link pointer of the new node is set to point to the node which is next to the given node. Figure depicts the steps involved in the insertion procedures. A new node, Z, is inserted after the node C. Inserting a node before a given node. The algorithm for inserting a node before a given node is slightly more complex than the node for inserting after a specified node. The reason is that in placing a new node in correct position, we need to readjust the link pointer of the node which is to precede the new node. Thus, we have to identify not only the given node, but also the node that precedes the given node. For this purpose, we use two pointers to scan the list. The first pointer is moved to identify the specified node. The second pointer trails immediately before the first pointer. In this way, when the first pointer ultimately reaches the given node, the second pointer points to the preceding node. We can use the second pointer to point to adjust the link pointer of the preceding node to point the new node, and then use the first pointer to reset the pointer of the new node to point to the given node. The procedure for inserting a node before a given node is depicted in figure. As will be seen, a new node Z is inserted before the node C. Observe that two pointers are used. One points to C and other to the preceding node B. The code for insertion algorithm is given in the demonstration that follows. Deleting nodes from a linked list. A major advantage of a linked list data structure is that it allows judicious use of storage space. A node which becomes redundant can be purged to release the allocated space. As with the insertion, the deletion operation can also be applied to the front, middle, or last node of a list. The algorithm varies slightly in each case. We now examine these cases separately. Deleting a front node. In order to delete a front node of a list, we create a pointer which is set to identify the first node. The head pointer is then moved to point to the next node. Using the pointer, we remove the first node. Figure illustrates the procedure for deleting the front node of a sample list containing A, B, C, and D. Deleting tail node. For deleting a tail node, we use two pointers, so that in traversing the list, the second pointer trail immediately before the first pointer. Thus, at the end of the traversal, the first pointer points to the tail node, and the second pointer points to the node that precedes the tail node. We use the second pointer to set the link pointer of the preceding node to null value, so as to sever its link with the tail node. Then, using the first pointer, we remove the tail node. The deletion procedure is illustrated in figure. Deleting a middle node. The algorithm for deleting a middle node is essentially the same as for deleting a tail node. We use two pointers to scan the list, such that one pointer immediately follows the other. After the given node has been identified by the first pointer, we remove its link to next node. Using same pointer, we set the link pointer of the preceding node to point to the node that is next to the given node. Finally, using the first pointer, we delete the specified node. Figure depicts the procedure for deleting a node C of a linked list that initially contains letters A, B, C, and D. Traversing a linked list. In traversing a list, we visit each node exactly once. Traversing is performed when we need to access information contained in the nodes of a linked list. Suppose we want to print the list or determine the size of a list, then traversal would be the natural procedure. In order to traverse a list, we normally use a pointer, which is initially set to point to the first node. After the first node has been processed, the pointer is set to move to the second node by using the link pointer of the first node. This process is continued until a node is encountered with link pointer containing a null value. We have already seen the use of traversal procedure in performing insertion and deletion. Figure shows another example of traversal algorithm. The code implements a method lSize, which returns size of a list with pointer head pointing to the front element. Briefly, these steps are involved. A counter is initialized to 0. A node pointer temp is used to point the first node. A loop is set up to scan the list. In each cycle, the counter is incremented by 1. At the end, the function returns the count value. Sorting a linked list. Sorting is another important operation which is sometimes required to be performed on a linked list. In order to sort a list, we systematically compare the contents of a pair of nodes and swap them if necessary to bring them in the given order. The important point to bear in mind is that only information fields of the nodes are exchanged. The link pointers of the corresponding nodes remain undisturbed. Figure lists the code for the sort method. Briefly, it performs these steps. Two node pointers, P and Q, are used to identify a pair of nodes. A nested loop is used to perform comparison and swap the elements to bring the node values in ascending order. A temporary array T is used to hold a data value to be swapped. Searching a linked list. We can perform a linear search on a linked list. In this operation, we start with first element of the list and systematically compare the contents of nodes with the value to be searched for. The operation is terminated when a match is found. If the list is already sorted, the search process can be abandoned after the node value is found to be greater than the value to be searched. If the list is not sorted, we would need to scan the list up to tail node. It is emphasized that unlike an array, the elements of a linked list cannot be accessed directly. Thus, an efficient sorting method called binary search, which uses a middle element, cannot be applied to a list. In the case of the list, there is no simple way of finding middle element. Performance of linked list operation. We now examine the time efficiency of the common operations associated with a linked list. We assume that the list consists of n nodes. Remember, in insertion and deletion operations, we simply readjust the link pointers. The information portion of a node is not affected. The modification of link pointers is not an expensive operation because no movement of stored data takes place. The efficiency of the operation depends on the number of times the list nodes are traversed. When a node is inserted at the front, running time does not depend on the size of the list. Thus, the operation has running time O1. If a node is inserted at the end, the nodes would need to be scanned n times, and at each step, one comparison of link pointer is made. As such, the running time of operation for inserting a tail node is On. If a middle node is inserted on an average of n/2, comparisons of the link parts will be made. Thus, efficiency of inserting a middle node is O(n/2) or equivalently On. The deletion operation essentially involves the same steps as with the insertion, except that two pointers are used. Thus, in general, two comparisons are made. The deletion of a tail node has efficiency O(n), or simply ignoring the multiplicative factor. In sorting a list, we use two nested loops. The outer loop is performed n times. In each iteration, we compare the pointers and set the next value for the index of the inner loop. In general, n-1 comparisons are performed in first iteration, n-2 in second iteration, and one comparison in the last iteration. Thus, altogether, the number of comparisons is as shown. The sort operation has time efficiency or equivalently. Advantages and disadvantages of linked list. The linked lists have several advantages over other data structures for storing data collection. In the light of preceding discussions, we can say that a single linked list has these merits. The size of storage space can be adjusted dynamically at runtime according to a particular application requirement. The insertion and deletion operations are comparatively fast because, unlike an array, the movement of data values within the storage cells is not required. Instead, only the pointers are readjusted. List traversal is extremely fast. The disadvantages associated with a linked list are: a linked list has an overhead of pointers which occupy additional storage space. The elements of a linked list cannot be accessed directly. Instead, one needs to scan the list in order to reach a particular element. Application of linked list. Linked list data structures are normally used to implement other complex structures such as trees, graphs, and heaps. Linked lists are also useful for creating dynamic stacks and queues. These topics will be covered in the subsequent units. Some compilers use linked lists to store and process polynomials. A polynomial is an algebraic expression in which powers of one or more variable appear in a summation. We consider a simple polynomial with a single variable. We can store the coefficients and associated power of variable into a node of a list. The nodes point to the subsequent elements of the expression. Figure shows an example of polynomial and the corresponding linked list. Notice that missing terms of polynomial are not considered in the representation. Using a linked list representation, a compiler can effectively perform the basic algebraic operations on the polynomial values. We can also use a two-dimensional arrays to handle polynomials. Figure shows such a representation. Observe, however, that missing elements in the polynomial must be explicitly represented in the array, because the array data structures does not by itself identify the next element. Array representation is not suitable when the polynomial is sparse, that is, when the polynomial has many missing elements. For example, the expression shown in figure requires just 3 nodes. Against this, a two-dimensional array would require 102 elements, most of which would contain zeros. Cursor implementation of linked list. The linked lists are normally implemented by using pointers or references to the storage location of the linked nodes. In C, C++, the reference pointers are explicitly coded, whereas in Java, implicit references are used. These implementations are often referred to as reference-based. However, some programming languages such as Fortran and Visual Basic do not support explicit or implicit pointers. It is nonetheless possible to use array data structure to implement linked lists. This approach is called cursor implementation. In the alternative method, two arrays are used to store the information fields and pointer fields. The pointer values are, in fact, the indexes of the information fields. By convention, -1 represents the index value for the tail node of the list. Figure shows an example of the cursor implementation of a sample list which contains characters A through H. The data array holds the characters. The second array, called pointer array, contains the indexes of the next elements in the data array. A variable front is used to identify the first element of the list. By using this information, we can traverse the data array and list all the elements. The corresponding linked list is also shown pictorially. Note that the elements of the array are sorted. A major drawback of array implementation is that size of list cannot be increased dynamically. Variation of linked lists. The linked list data structure that we have studied so far is known as regular list. There are several variations of the basic form of list which are useful in different situations. Some common types are circular linked lists, doubly linked lists, circular doubly linked lists, list of linked list or multilist. We now briefly examine the salient features of these data structures. Circular linked list. We have seen that in a regular linked list, we can traverse the nodes in one direction. We cannot go back to any of the preceding node unless we retrace the head node. This is a major drawback. A circular linked list overcomes this limitation. In this structure, the link pointer of the tail node is modified so that it points to the front node. The modified structure is referred to as circular linked list. In this data structure, we can continuously scan the list so as to reach any of the nodes. A circular linked list has no front or tail node. However, in order to make entry into the list, we need to reference one node using an external pointer. As with the regular list, this pointer may be referred to as head pointer. When the list is empty, the head pointer contains a null pointer. Figure shows an example of a circular list containing characters A through F. A circular linked list can be used to represent processes which are executed in cycles. For example, an operating system might use a circular list for round-robin scheduling of tasks. As with regular lists, we can perform basic operations of insertion and deletion on a circular list. Advantages and disadvantages of circular linked list. A circular linked list has these advantages over the regular linked list. Any node can be designated as the first node in the list. Each node is accessible from any other node. A circular linked list is more suited to process strings using concatenation and splitting operations. A limitation of the circular list is that unless the starting node is properly tagged and identified, a traversed operation might go into an infinite loop. Basic operations on doubly linked lists. The basic operations that can be performed on a doubly linked list include insertion, deletion, traversal, sorting, and searching. Their implementations are similar to the ones for regular lists. A significant difference is that in scanning the list, we can perform bidirectional traversal. Also, we need to make adjustments of left and right link pointers. We briefly examine the insertion and deletion operations. Inserting a node into doubly linked list. A new node can be inserted at the front, in the middle, or at the tail of the list. The procedure for inserting a front or tail node is similar to the procedure for a regular linked list. We create a new node. This node is linked to the pre-existing front node or tail node by readjusting the left and right pointers. A similar procedure is followed to insert a node in the middle of the list. We use a pair of temporary pointers to scan the list. The second pointer trails behind the front pointer. Thus, when the scan pointer points to the given node, which will be preceded by the new node, the second pointer points to the immediate predecessor of the given node. After the given node and its preceding node have been identified, the link pointer of these nodes are adjusted to link them to the new node. Figure illustrates the insertion procedure of the original list, which consists of nodes containing letters A, B, C, D. A new node Z is inserted before the node containing letter C. You may wonder why we need two pointers when a link to previous node is already known. Actually, although we can access a preceding node, we need an external pointer to make adjustment in the link pointers. Deleting a node from doubly linked list. In order to delete a given node, we first locate the node. Then, the link pointers of the succeeding and preceding nodes are adjusted to break links with the given node. The deletion process is illustrated in figure. The original list contains characters A, B, C, and D. The node C is removed from the list. Advantages and disadvantages of doubly linked list. The main advantages of a doubly linked list are: It allows a bidirectional traversal for processing nodes. Insertion and deletion are fast. A sorted list can be printed in either ascending or descending order. The major drawback of a doubly linked list is that additional storage space is required for the link pointers. Also, the address of the preceding and succeeding nodes needs to be closely tracked to avoid misdirected traversals. Circular doubly linked list. A circular doubly linked list is a variant of the doubly linked list. As the name implies, in this data structure, the next link pointer in the tail node contains pointer to the first element. Also, the previous link pointer in the first node points to the tail node. An example of a circular doubly linked list is shown in figure. Since there is no first and last node in a circular list, we choose an arbitrary node for making entry into the list. An external pointer identifies this node. A circular doubly linked list inherits all the advantages of a circular and doubly linked list. We can access the nodes from a given node. Further, we can traverse the list in forward and backward directions. The disadvantage is that the link pointers need to be closely monitored to avoid the risk of endless looping through the list. Multilist. We can combine a set of related list structures into an integrated linked list called multilist. In this way, we can easily access all the nodes in one list that are related to given node in the other list. Consider, for example, a list that contains student records and another list that contains subject information. We can combine these lists into a multilist so that we can access all the students that are registered in a given subject. Conversely, we can access the subjects in which a particular student is registered. In order to build the multilist, we need additional link nodes that link students with subjects. Thus, the list would contain these nodes. Nodes that contain subject data and link pointers for subject. Nodes that contain student data and link pointer for student. Link nodes that connect subjects with students. An example of the multilist is shown in figure. The subject and student links are circular. The labels std1 and std2 and so forth are head pointers to student links to the subjects. Likewise, sub1 and sub2 and so forth are head pointers to subject links to the students. It is assumed that each student can register in 2 courses. As shown, the first student is enrolled in the first and the third subject. Observe that a multilist can be traversed to list students by a given subject or the subjects taken by a given student. Introduction. In this unit, we introduce a fundamental data structure called stack. The unit begins with the description of inherent characteristics of stack data structure and associated operations that can be performed on it. The working of fundamental operations is illustrated with the aid of visual presentations and animation. The unit describes how a stack can be implemented using array and linked list. Besides, the performance issues relating to different implementations are elaborated. The unit concludes with a detailed description of stack applications in computer science and other disciplines. Objectives. On completion of the unit, you should be able to define a stack and its characteristics, Describe basic operations of push and pop and the associated conditions for their applicability. Implement a stack using static and dynamic allocation of memory. Compare the relative performance of each implementation. Describe how stacks can be used in different applications. Understand the use of stacks for parsing of character strings. Distinguish between infix, prefix, and postfix notations used to represent algebraic expressions. Explain how stack can be used to convert infix expressions into postfix notation. Understand the algorithm for evaluating arithmetical expressions with the aid of stack. Describe how stacks can be used for implementing subprograms calls. Understand the role of stack in recursive function calls. Introduction to stacks. A stack is an ordered collection of homogeneous data items in which addition of new items and removal of existing elements can take place at one end. The entry or exit point is referred to as top. The operation of adding an item to a stack is called push, and that of removing an existing item is called pop. Clearly, a stack is a dynamic data collection which work on the principle that an item added last is removed first. For this reason, a stack is also known as last in, first out, LIFO data structure. A stack has analogy with some special arrangements of certain objects used in our daily life. Familiar examples are piles of trays in a self-service cafeteria, stack of plates on a dining table, bundles of office files in in-out trays, and arrangements of letters in mailboxes. In each case, the object at top is accessed first by any user. It does not make sense to pull out an object from the middle or bottom of the pile. Let us look at a simple example to understand the working of a stack. Figure shows 3 states of a stack, which stores a set of alphabets. First figure shows the state with 4 elements A, B, C, D, with D at the top. Second figure shows the state after D has been popped off the stack. Last one indicates the state after E has been pushed onto the stack. Note that a stack data structure has some distinct features. First, it is collection of homogeneous items. This means that all data items must be of the same type and size. The elements may not necessarily be of the primitive types. These can even be complex data structure like records. Second, the elements in a stack are ordered, which implies that data are stored in certain sequence, which is determined by the frequency of insertion and deletion. The order is not visible to the user. Third, a user cannot have a direct access to an item except one at the top. A user, for instance, cannot retrieve an item from the middle or bottom of stack collection. Finally, in principle, a stack can hold any number of items. However, in practice, there is always an upper limit to stack size due to limitation of available memory in the computer. Operations on stacks. We have already mentioned the 2 basic operations, which involves addition and deletion of data items stored in a stack. In standard terminology, these operations are called push and pop. There are other auxiliary operations which are sometimes useful in manipulating stacks. These are referred to as isEmpty, isFull, and getTop. Let us explore these operations and examine the circumstances for their applicability. Push operation. The push operation inserts or pushes a new data element onto the stack. In certain implementations, there is a restriction on the number of items that can be added to the stack. In this situation, prior to executing the push operation, it must be checked if stack can accommodate a new item. Pop operation. The pop operation removes an existing item from the top of stack. To avoid error condition, before applying the pop operation, it must be ensured that the stack is not empty. Get top operation. The get top operation returns a copy of the data item at the top of the stack. The item itself is not removed from the stack. This operation is sometimes called peek. IsEmpty operation. The isEmpty operation returns true if the stack contains no element and false otherwise. It is normally applied before pop operation to avoid stack underflow condition. IsFull operation. The IsFull operation returns true if the stack is full and cannot accommodate new items. Otherwise, false is returned. This operation is usually performed before the push operation to avoid stack overflow condition. It is not used when a stack is implemented using dynamic allocations of the storage, since space is automatically provided out of heap memory for any new entries in the stack. In addition to data manipulation operations, all applications invariably need the operations for creation and destruction of stack objects, which are called create stack and destroy stack. The create stack operation creates an empty stack. The operation is normally used at the beginning in any application using stack. The actual implementation determines how the stack is initialized at the time of creation. The destroy stack operation removes all elements from the stack and releases the memory space previously allocated to the stack data structure. Stack implementation. You would recall that implementation of an abstract data type involves developing necessary code for the associated methods and data objects. The ADT provides the framework for the implementation in the shape of an interface. In the context of a stack, essentially two schemes for the implementations are followed. These are called array-based and linked list-based implementations. The latter is also known as pointer or reference-based implementation. We now look at these schemes in a greater detail using C++ classes. The code fragment is shown on the screen. Array-based implementation of stack. In this approach, an array of appropriate data type or data structure is used to hold the elements of a stack. The declared size of array determines the maximum number of elements that can be accommodated in the stack. A variable top is used to identify the element on top of the stack. It is initialized to -1 to indicate an empty stack. The elements of stack are placed in a sequential order in the consecutive cells of an array. By convention, the first element that enters in the stack is placed in the first cell, the second in the next cell, and so forth. When an element is pushed onto stack, the value of variable top is incremented by 1. An incoming element is placed in the array cell with new index top. Likewise, when an element is popped off the stack, the array cell currently identified by top is accessed and returned, and top is decremented by 1. An array representation of stack is shown on screen, which can hold 10 stack items. Initially, the stack contains 4 elements A, B, C, and D. The variable top holds the index value 3. When item is removed, the index value is decreased to 2. Figure also shows the empty and full states of the stack. Note that after an element is popped off the stack, only the variable top is decremented. The element may stay in the array as it would be overwritten when a new element is added. Thus, the value held by variable top rather than occupation of array cell determines the current status of the stack. This is more clearly shown in this figure, which represents an empty stack even though all the cells are shown to be occupied by previously removed elements. For example, if a new element K is pushed onto the stack, it would overwrite the element A in any cell with index 0. Of course, in a particular implementation, the cell can be initialized to null value if an item is removed. This would amount to extra work with no additional gain. Linked list implementation of stack. The array-based implementation is simple and straightforward. However, it suffers from a serious drawback. The size of the stack array needs to be specified at compile time. Generally, a fixed upper bound for the ultimate expected size of stack is assumed. If an application requires much less space than a maximum size, a lot of memory space would be wasted. On the other hand, if at runtime the storage requirement exceeds the size of stack array, the application would crash. Thus, array implementation is not suitable in circumstances where stack size cannot be predicted in advance. The linked list implementation provides a better alternative solution. In the linked list design, the stack elements are stored using nodes and pointers. An example of linked representation is shown on screen. Stack stores characters A, B, C, D with D at the top. The list header pointer top points to the top element in the stack. Internally, the elements of stack are linked together using pointers. The bottom element contains null pointer. The list-based implementation has the advantage that stack can grow or shrink according to application needs. Various stack operations are performed on the front element of the list. The push method simply adds a new front node. The details of procedures for adding a node to the linked list were discussed in previous unit. Briefly, to insert an item to the front of the list, following steps are followed. Number 1. Create a new node. Number 2. Copy new element into the node. Number 3. Assign pointer of new node to point to the element next to the top. Number 4. Assign existing top pointer to the new node. Figure shows the process of pushing an element E to the stack. The pop is implemented as to remove the front element of the linked list. The steps are summarized as followed. Number 1. Copy the contents of the front element into a variable which is to return the popped value. Number 2. Assign a new pointer to the top pointer. Number 3. Set top to point to next element in the list. Number 4. Delete the node. This figure shows pictorially the steps involved in the popping operation. The isEmpty method simply checks whether or not the head pointer to the list is set to null. The getTop simply copies and returns the content of the front node. The node is not removed. Performance of stack implementation. We have seen that array implementation of a stack is simple, short, and efficient. It provides direct access to the topmost element in array. The array implementation is most suitable for applications involving a small number of stack elements of known size. By contrast, the linked list implementation is more complex. It involves creation and deletion of front node in the list. Additionally, data is either copied or removed from a node using pointers. The list-based representation is preferable when the size of a stack is totally unpredictable. In both implementations, the amount of storage space is directly proportional to the number of elements in the stack. Thus, in big O notation, the space efficiency of either implementation is O of n, where n represents total number of elements in the stack. Let us examine the time efficiency of the two implementations. In array implementation, all stack operations involved manipulation of only the topmost element in the array. Since accessing of the topmost element is independent of the number of elements in the array, the time efficiency of all stack operation is O of 1. As with array representation, the list-based implementation also involves adding or removing a single node at the front. Since probing or accessing the header node is independent of the number of nodes in the list, the operation of insertion, deletion, or checking the top element have time efficiency O of 1. The destroy operation alone has time efficiency O of n because it involves removing n nodes from the memory to release the space. The time efficiency of different stack functions for both the implementations is summarized in the table. Stack application. Stack is among the most widely used data structures. It also forms the basis of other complex and advanced data structures. Stacks are extensively used in a host of computer applications. They play a central role in program compilation and translation of high-level languages. The fundamental compilation processes, such as checking the syntax of statements and conversion of arithmetic expression for evaluation by the computer, rely heavily on the use of stacks. Stack also play a crucial role in the implementation of subroutines and function calls. Stacks are indispensable in coding of recursive procedures. Many search algorithms employ stacks to backtrack to previous states. Stacks find common use in several computer applications such as text editors, web browsers, and image manipulation softwares. Now we examine in some detail the use of stack for parsing of arithmetic expressions and their evaluation by the computer. Later, we shall briefly review some other applications. Using stack for parenthesis matching. Parentheses are often used in arithmetic expressions to specify the priority of evaluation. A pair of parentheses is also used in some programming languages such as Fortran and BASIC to enclose index of a dimensional variable. In a syntactically valid expression, each left parenthesis must match with the corresponding right parenthesis. A simple counting of left and right parentheses would not provide a correct solution. For example, this expression has same number of left and right parentheses, but it is obviously illegal. We can use a stack to validate an expression by checking that for each left parenthesis there is a right parenthesis in the correct position. Here is the algorithm. Number 1. Scan the expression from left to right. Number 2. If a left parenthesis is encountered, push it onto the stack. Number 3. When a right parenthesis is found, pop the stack. If stack is empty, report a mismatch right parenthesis. Otherwise, pop the stack and discard popped left parenthesis. Number 4. At the end of scan, if stack is not empty, report an error. This algorithm can also be used for matching other symbols such as curly braces and square brackets. Recall, braces are used in Java and C, C++ to enclose a group of statements. Conversion of infix expression to postfix notation. We now examine how a stack is used by the computer to evaluate an arithmetic expression. In a high-level language, an arithmetic expression consists of variables and constants called operands and symbols for arithmetic operations. By convention, these operations have the following order of precedence. Number 1. Exponentiations are performed first. Number 2. Division and multiplication are performed next. Number 3. Addition and subtraction are performed last. Number 4. When two operators of the same precedence appear consecutively, evaluation takes from left to right. Number 5. Parentheses may be used to enhance the level of precedence. Examples of simple arithmetic expressions are a plus b, a minus b, a static b, a slash b, and so on. The algebraic notation for arithmetic expression is called infix notation. In this notation, an operator is placed between a pair of operands. The infix notation is not suitable for computer evaluation. To simplify the processing steps, two alternative representations are used, which are called prefix and postfix notation. In the prefix notation, the operator symbol is placed before the operands. For example, the infix expressions are written in prefix notations as shown. The prefix representation is also called Polish notation in honor to its inventor, Polish mathematician John Lukowicz. A complex arithmetic expression can be converted to prefix notation by processing the brackets and operators in order of their priority. For convenience, square brackets may be used to indicate partial conversions. Here is an example. In another notation called postfix or reverse Polish notation, the operator symbol is placed after the operands. For example, the infix expressions are written in postfix notations as with the prefix representation, the infix expression can be converted step by step by partially converting the operators and brackets according to their precedence. For example, this infix expression is translated to postfix as follows. Notice that postfix expression has following features. Number 1. All operands have the same order as in the infix expression. Number 2. Parentheses are not required. Number 3. Postfix expression is not the reverse of its equivalent prefix expression. Visual conversion of infix expression to postfix notation is awkward and prone to errors. A better way is to use stack for intermediate or partial conversion. To this end, we can use an algorithm which is based on the observation that in postfix expression the operators maintain their order and that operators of higher precedence should be evaluated first. Also, since left and right parentheses are not required in the postfix representation, these should be discarded after partial processing. The conversion algorithm consists of following steps. Number 1. Scan the infix expression from left to right. Number 2. When an operand is encountered, append it to the output string for postfix representation. Number 3. Push each left parenthesis onto the stack. Number 4. When an operator is encountered, check if stack is empty. If so, push it onto the stack. Otherwise, pop operator of the greater or equal precedence from the stack and append it to the postfix output string. Continue popping until either left parenthesis is encountered or an operator of lower precedence is at the top or stack is empty. Number 5. When right parenthesis is encountered, pop off the stack and append the popped operator to the end of output string. Continue with this process until a matching left parenthesis is encountered, which should also be popped and discarded. Push the new operator onto stack. Number 6. When the scanning process is complete, pop off all operators from stack and append them to the output string. The algorithm appears to be overwhelming for manual conversions. It is, however, better suited for machine conversion. To understand the working of algorithm, consider the conversion of following infix expression. In this expression, caret symbol indicates exponentiation. The conversion steps are as shown on screen. Notice that up to step 8, all operands are appended to the output and operators are pushed onto stack. At step 9, right parenthesis is encountered and as consequence, minus and left parentheses are popped. The minus operator is popped and left parenthesis is discarded. At step 10, slash is encountered. As a result, asterisk, which has the same priority as slash, is popped and appended to the output, and slash is pushed to the stack. At step 12, plus is encountered, which has lower priority than slash in the stack. Thus, slash and plus of equal priority are popped and appended to the output, and new plus is pushed to the stack. At step 14, caret is encountered, which has higher priority than plus in the stack. It is therefore pushed to the stack. At step 15, the scanning of infix expression is complete, and therefore plus, caret, currently in stack are popped off and appended to the output. In this way, the infix expression is converted to postfix expression. Evaluation of arithmetic expression using stack. We have stated before that arithmetic expressions in algebraic notation are not suitable for evaluation by the computer. Generally, an expression in infix representation is evaluated in 2 steps. First, it is converted into an equivalent postfix expression by using the algorithm previously explained. Next, the variables in the postfix expressions are replaced by their current values. Finally, the postfix expressions with numerical operands is evaluated. The last evaluation is carried out using stack to save the intermediate results. The algorithm for computation involves following steps. Number 1. The arithmetic expression in postfix notation is scanned from left to right. Number 2. If a numeral is encountered, it is pushed onto the stack. Number 3. If an operator is encountered, two operands are popped off the stack and the current operators is applied to the operands. Number 4. The result is pushed onto the stack. Consider, for example, the infix arithmetic expression. In postfix notation, it is written as: using the previous evaluation algorithm, the postfix expression is processed. The evaluation steps are depicted in figure. Use of stack in function calls. A stack plays a pivotal role in the execution of function calls. When a function is invoked, program control is transferred to entry address of the called function. After the function has been executed, the control is transferred to the next instruction in the calling program. The function calls can be nested, which means that a function can, in turn, call another function. In this process, the system must remember the addresses where to backtrack after the call function has been executed. Therefore, the return addresses and the local variables must be saved and retrieved in the reverse order. This task can be performed most efficiently with the aid of a stack. When a program or function calls another function, its arguments, the return address, and values held by the local variables are pushed onto the stack. After the call function is executed, the saved data is popped off the stack and control is transferred to the popped address. A data structure that holds the function parameters, local variables, and the return address is commonly known as stack frame. Almost all compilers for high-level programming languages make use of stack frames to process function and subroutine calls. An example of function calls and working of stack frame is shown in the figure. The function main calls a function alpha. The function alpha in turn invokes function beta. After beta has executed, the control is transferred back to alpha. When alpha has been executed, the control is transferred to main. At each stage, the value passed as arguments to the function, its address, and values of local variables are preserved in the stack frames. On backtracking, these are popped off the stack frames and returned to the calling function. Use of stack in recursive procedures. A procedure in which a function calls itself is called recursion. It is a powerful technique which is extensively used in concise description or solution of a problem. For a recursive procedure to be useful, it must satisfy two conditions. First, each procedure call should bring it closer to the solution. Second, there must be a decision point at which the procedure should terminate. A recursive procedure that satisfies these conditions is said to be well-defined. Since a recursive procedure is generally implemented in 3 steps, which are known as prologue, body, and epilogue. In the prologue step, the function arguments, local variables, and return addresses are saved by pushing them onto a stack. In the body step, a base criteria is used to determine whether or not the recursion should terminate. If so, the epilogue step and prologue step is invoked again. In the epilogue step, saved parameters, local variables, and addresses are popped off the stack and used to perform the intermediate computations. A simple example of a recursive procedure is the evaluation of a factorial. You would recall that the product of successive positive integers is called factorial. Consider, for example, the evaluation of the function factorial of n. If n equals 4, the recursive steps would be as: by backtracking the above steps, we can obtain the value of factorial of 4. An example of C++ function that can be called recursively to compute factorial of a given number is as shown. Use of stack in application software. Stacks are commonly used in the implementation of several application packages. Current generation of desktop applications such as word processing, spreadsheets, graphics, and image processing include feature to cancel any previous processing steps. In word processing, for example, any changes to a currently open document are pushed onto the stack. When the undo option is exercised, the changes are popped off the stack and applied to the current version to revert to the old version of the document. The web browser frequently uses stack to maintain a history of visited sites or downloaded web pages. As the web pages arrive, they are pushed onto the stack. Later, if a user clicks the back button, the stack is popped off to display the most recently downloaded page. In the same way, the browser can retrieve the most recently visited sites. Stack machines. Because of their frequent use in several computer science disciplines such as compilers, interpreters, and operating systems, stacks are increasingly being implemented in the hardware architecture. Originally, this facility was built into mini-computers such as PDP-2 and Burrow 5000. For this reason, these computers were commonly referred to as stack machines. Currently, most CPUs, such as Intel and Motorola processors, have built-in features for stack. The instruction set for these processors include push and pop mechanism. A push instruction causes the contents of specified memory location to be saved in the stack register. The pop instruction removes the top entry in the stack register and places in the main memory. Some microcontroller used in industrial commercial applications also employ stack for rapid processing of data in real time. Unit Overview. In this unit, we turn to another important data structure called queue. We shall study characteristics of various types of queues and related operations. We shall also examine various applications of queues in daily life, computer science, and other disciplines. For each type of queue, we would study different ways of implementing queue data structures using arrays and linked lists. Objectives. After studying this unit, you should be able to define the logical structure of a queue, understand the operation involved in adding elements to a queue and removing items stored in a queue. Describe circumstances when underflow and overflow conditions occur in manipulating queues. Describe simple applications which make use of queue data structure. Distinguish between regular queues, circular queues, priority queues, and dequeues. Understand the array-based implementation of different variants of queues. Understand the linked-based implementation of regular queues and dequeues. Compare the relative advantages and disadvantages of different implementations of queue structures. Choose appropriate implementation on the basis of performance and efficiency. Introduction to queues. A queue is a collection of homogeneous items in which new items can be added at one end and current item removed from another end. The end at which an item is removed is called front, and the other end at which the item is appended is called rear or back of a queue. A queue acts like a tunnel, such that an element entering first comes out first. For this reason, a queue is commonly called first in, first out, FIFO structure. A FIFO queue is sometimes called a regular queue to distinguish it from other variants of queue. Figure shows an example of queue which contains alphabets A through H. The arrows mark the front and rear ends of the queue. Notice that there is only one entry and one exit point. This arrangement implies that only the front and rear elements of the queue can be accessed directly. The middle elements are not accessible, and their order is preserved in all operations on a queue. This feature is illustrated in figures. In the first example, letter A is removed and the front pointer moves to the element B. In the second illustration, letter I is added and rear pointer is moved to the newly entered alphabet. Notice that after addition and deletion, the order of elements B through H remains unaltered. Remember, as with other data structures, the elements of a queue must be homogeneous. This means that all items must be of the same data type and size. However, elements may not necessarily be numeral, character, or other primitive types. Depending upon the application, a queue data item can be records, consisting of several fields, or even more complex data structures. For example, a queue representing the telephone directory might contain subscriber's name, address, and telephone number. Application of queue. Various forms of queues are often observed in our daily life. Some familiar examples are a line of persons waiting for their turn to board a bus, utility bill payers standing in a queue to make payment at bank counter, a fleet of cars and buses lined up at a toll booth on motorway. In all of these examples, the principle of first come, first served applies. All new arrivals must join at the rear of the queue. Different types of queues are extensively used in computer sciences and other disciplines. Queues provide an effective buffering mechanism for synchronizing the operation of slow devices with fast CPU. For example, the keyboard is a slow device compared to other processing units of a computer. Thus, when we enter characters at a keyboard, the computer system holds these characters in a buffer, in the order in which the characters are typed in. The queue is later processed by CPU or displayed on the screen. Likewise, in printing jobs, the computer sends lines and images faster than the printer can print them. The lines and pixels are held in a queue for the printer and processed in the order in which they enter the buffer. Also, when a printer is shared by several computers, or when a desktop computer sends several printing jobs, each job is inserted at the rear of print queue. Queues are frequently used by operating systems for sequencing and scheduling of events, messages, processes, and subtasks in time-sharing environment. In operation research, queuing models are used to analyze and optimize the service times by minimizing the waiting time and reducing service cost. Operations on queues. Some common operations on a queue include creating a queue, adding new item to a queue, removing an item, checking if queue is empty, checking if queue is full, determining number of elements in a queue, accessing the first added item without removing it from the queue, destroying the queue. Creation of queue is always the first operation in any application. This step simply creates an empty queue. The add operation inserts a new item into the rear of a queue. If the space allocated for the queue is already utilized, this results in overflow condition. The add operation is also called enqueue, insert, or append. The remove is another primitive operation associated with the queue. This operation removes the item at the front of the queue. If queue is empty, an underflow condition occurs. To avoid this problem, queue must be checked for emptiness. The remove operation is also known as dequeue, delete, or serve operation. The operation returns the retrieve item to the calling application. The isEmpty operation returns true if the queue is empty and false otherwise. It is generally applied to check the underflow condition. The isFull operation checks if the queue currently contains the maximum number of allowed items. If the limit is reached, the operation returns true and false otherwise. The sizeOf operation returns the number of elements currently held by a queue. The peek operation returns the item that was last added to the queue. However, unlike the remove operation, the item is not deleted from the queue. The destroy operation removes all elements of a queue and releases space allocated to the queue. Implementation of queue. There are two approaches to the implementation design. A queue can be stored in static array of fixed size or dynamically allocated memory using linked lists. Both schemes have their advantages and disadvantages. In general, the queue data structure is implemented as a C++ class which has the composition as shown. Note that a class queue includes two integer variables, front and rear, which monitor the exit and entry points of a queue. The coding details of class methods add, remove, isEmpty, isFull, peek, and destroy are covered in subsequent sections. Array-based implementation of queue. In array-based implementation, an array is used to store data items in a queue. For example, if we may want to store names in a queue, the declaration might look like this. This declaration is meant to store 100-character strings called queue names. The maximum size of a data item is assumed to be 20. Remember, in C, C++, the character strings are declared as a two-dimensional character array. Also, we need to declare two integer variables, front and rear, to indicate the position of an item to be added or to removed from the array. The variables are initially set to -1. As data are added to the queue, front and rear are incremented by 1. Figure shows an example of array-based implementation to hold up to 10 elements of a queue. As shown, the queue holds 5 characters Q through U, which have array indexes from 1 to 5. The variable front contains 1, which is the current position of the elements at the front position, and variable rear contains 5, which indicates the last position of the queue. The next figure shows a full queue. Performance of array-based implementation. As insertion and deletion operations in the array are controlled by the variables front and rear, the performance of these operations does not depend solely on the number of data items in the queue. As such, the running time of both NQ and DQ operations is O of 1. Limitation of array-based implementation of queue. A major limitation of the array-based design is that the maximum size of the queue must be specified in advance. If a user needs a queue to process fewer items than the prescribed size of array, a lot of memory space would be wasted. Another serious drawback of the array-based scheme is that the slots created by removing of items from an array cannot be filled by the new incoming items. Consider the queue shown. In this example, the array elements with indexes 0, 6, 7, 8 and 9 do not hold any queue items. Since elements can only be added at the rear end, the array elements with the index 0 cannot be filled with the new element. Further, as new items are added or current items deleted, the entries in the array shift to the right. This behavior is shown in figure. After P, Q, R have been removed and U, V, W are added. Ultimately, if all the elements are removed, both front and rear would move to the rightmost position. It would result in a situation in which the queue is empty and yet no new elements can be added to the queue. One possible solution to this problem is to shift all the elements to the left whenever an item is removed from the queue, as shown. The new elements can always be added to the vacant position on the right. Further, we would no longer need front pointer because the elements of array index 0 will always be the first element of queue to be deleted. However, for very large queues, the process of shifting all the elements at each deletion would time-consuming. It would have a running time O of n for a queue of size n. Thus, though the alternative array representation would be space-wise economical, it would not be time-wise efficient. A satisfactory solution for efficient utilization of array space is provided by wrapping round the front and rear pointers to the beginning of the array. This strategy is called circular implementation. The corresponding queue is known as circular queue. We shall examine circular queue later in this unit. Linked list-based implementation of queues. We have seen that array-based implementation does not provide a satisfactory solution to handle queues of variable sizes. An alternative approach using linked list overcomes these problems by dynamically allocating storage space. In this implementation, elements of queue are stored as nodes of a linked list. 2 pointers are needed to mark the beginning and end of a queue. These are referred to as front and rear pointers. Figure shows an example of a queue implemented as a linked list. Implementation of NQ and DQ operations is rather straightforward. The NQ simply adds a node at the tail of the linked list. The DQ operation removes the first node of the list. The detailed procedures for adding and deleting nodes of a linked list were discussed in the previous unit. To recapitulate, in order to add a new element to the queue, we create a new node, copy queue data into the new node, set the link pointer of new node to null, set the rear pointer to point to the new node. To remove an element from the queue, we proceed like this. Create a temporary node pointer and initialize it with front pointer. Create a temporary node and copy the contents of head node to the temporary node. Reassign the front pointer to point to the next node. Delete node pointed to by temporary pointer. Return the copied information. Circular queue. In the circular queue, when the rear or front pointer gets to the last element in the array, it is wrapped around or reset to the first element, provided it is not already occupied. An example of circular queue is shown in the figure, which shows the initial state and subsequent states after addition and deletion of elements. Although inside the computer, the elements of the circular queue are stored consecutively in a linear order, it is intuitively more appealing to display them in a circle or ring shape as shown. In practice, the circular queues are more commonly used than the linear queues. Operating systems use circular arrays to implement the round-robin scheduling policy for process management. In computer networks, switches and routers use circular queues to store and forward packets of information. Array-based implementation of circular queues. You must have observed that the operations associated with the circular queues are identical to those on linear queues. However, there are few differences in the implementation of isFull and add operations because of overflow and underflow conditions. The overflow condition can occur in these circumstances: when the rear pointer is positioned at the last element of the array and the first element of the array is occupied, when front pointer is one element ahead of the rear pointer. These conditions are illustrated in the figure. Notice that in the first case, the rear is positioned at the last element with array index 7, while the first element of the array with index 0 is already occupied. In the second case, rear is positioned at the array element with index 2, while front is positioned at array element with 3. In both cases, it is not permissible to add a new element. Thus, in implementing the isFull and add operations, we must check for these conditions. Priority queues. The queue data structures which we have considered so far operate on the basis of first-come, first-served principle. There are, however, certain applications which require retrieval and processing of queue elements according to some prescribed order. For example, in some situations, it might be desirable to remove the last item first, bypassing all other items in the queue. The solution to such problems is provided by the priority queues. A priority queue, like an ordinary regular queue, is a collection of homogeneous data items in which items are added at one end and removed from the other end, but on the basis of priority. Thus, each item of a queue contains a data field and a priority field. The items within the queue structure are kept sorted according to the priority key. This figure shows an example of a priority queue. In the example, the queue consists of letters E, D, R, Z, and A with the priorities 1, 1, 2, 2, and 4 respectively. The elements will be removed in the same order. If another element, say Q, with priority 2, is added to the queue, it will be placed after the element A and before the element Z. The new state of Q is shown in figure. When a new element has the same priority as that of some of the existing elements, the principle of FIFO applies. For example, if an element T with priority 2 is added to the queue in figure, it is placed before Q, which also has priority 2, as shown. Applications of priority queues. Priority queues are often used by operating systems for managing and scheduling of processes in CPU. In preemptive multitasking operating system, tasks are placed in a priority queue which are processed according to their priorities. Programming languages supporting multi-threading use priority queue to control the execution of threads. In VLSI circuit design, channel routing and pin layout are efficiently manipulated by the priority queues. Priority queues are also used for controlling mission-critical applications such as industrial plants, nuclear reactors, or space vehicles. In an industrial plant, for example, working of various components is monitored and shown on the console. All events and associated messages are buffered in a priority queue. Appropriate actions on the processes with the highest priority are initiated immediately to take necessary remedial measures. Implementation of priority queues. Generally, a priority queue is implemented by using any of the approaches: array-based design, linked list design, binary tree, or heap design. The binary tree provides the most efficient implementation. For example, the time efficiency of array and linked list implementation is O of n, and that of binary tree implementation is O log n. Here, we consider the array design, which is comparatively simpler. Array-based implementation of priority queues. In this implementation, we assume that Q will be stored in an array of character strings with associated priority and sequence numbers. The C++ interface for the queue would look like this. Double-ended queue. An enhanced and more flexible version of queue is called DQ, which is pronounced as DEC or DQ. It is a collection of homogeneous data items in which data can be added to or removed from two ends. Thus, a DQ has the behavior of a stack as well as that of a queue. This figure shows an example of DQ. The second figure shows another state of the DQ after G and T have been removed from the queue and Z and W are added. Note that the order of the elements within the queue is not disturbed on account of new additions or deletions. To mark the ends of a DQ, two pointers, front and rear, are used. In some applications, it is necessary to restrict the entry or exit points of a DQ. A DQ in which addition can be made at only one end and deletion at both ends is referred to as input restricted DQ. Similarly, a DQ which allows deletion at one but addition at both ends is called output restricted DQ. Implementation of DQs. A DQ can be implemented using an array or linked list. In the array-based implementation, usually a circular array with two pointers variables, rear and front, are used. The size of array and type is fixed at compile time depending upon the expected number of elements and data type of queue items. When an element is added to the DQ at the front, the variable front is decremented by 1, and if it is added at the rear, the pointer is incremented by 1. Conversely, when an item is removed from the front, the value of front is increased by 1, and when an item is removed from the rear, the value of rear is increased by 1. When the queue is empty, the variables rear and front are set to null values. In the linked list implementation, the elements of DQ are contained in the linked nodes. Two pointer variables, rear and front, are used to mark the rear and front entries in the DQ. When an item is added, a new node is created at the head or tail of the list depending upon the entry point. Likewise, the head or tail node is deleted when an element is removed from the front or rear of the DQ. Unit Overview. In this unit, we introduce an important data structure called tree, which is extensively used to represent hierarchical relationship. This unit begins with an introduction to general trees and elaborates basic definitions and tree terminologies. It mainly focuses on binary trees and their variant forms, namely binary search tree and expression tree. It provides exhaustive description of binary trees, including basic concept and actual implementation of tree operations. Unit Objectives. After completing the unit, you should be able to understand the vocabulary and terms relating to tree data structure, describe properties of general trees and their applications, explain the distinguishing features of binary search trees, heap, expression trees, red-black trees, and decision trees. Understand the difference between pre-order, in-order, and post-order traversal of binary tree. Become conversant with the implementation of traversal algorithms using recursive procedure. Understand the significance of binary search trees for sorting and searching problems. Recognize significance of balanced trees and unbalanced trees and the associated performance issues. Introduction to trees. A tree is a data structure in which data elements have hierarchical relationship. There are several ways of describing the internal structure of a tree. Formally, we can define a tree data structure as a collection of data elements called nodes, such that the collection has a special node called root, which provides an entry point to the tree data structure. The nodes are connected together with edges or paths. There is exactly one path from the root to any node in the tree. A tree data structure is often depicted by means of a diagram. Unlike a natural tree, a tree data structure is shown to grow from top to bottom, with the root at the top and leaves at the lowest level. A node is represented by a circle, oval, or rectangle. It is usually labeled with the data value contained in the node. The edges are shown by the slanted lines. By convention, tree is portrayed from top to bottom. The direction of edges is therefore omitted. Figure shows an example of tree data structure. In this structure, A is root node. E, M, N, G, H, I, J, K, L are leaves. All other nodes are the internal nodes. Basic definition and terminology. The structure and properties of a tree structure are described by using a special vocabulary which is borrowed from mathematical graph theory and family trees. Most algorithms for trees use this terminology. We therefore have a closer look at these terms. Parent node. In the tree hierarchy, a node directly above a given node is called parent node. C is the parent node of H, I, and J. The only exception is the root node, which has no parent. Child node. A node which is directly below a parent node is called child node or simply a child. For example, C is the child of root and H, I, J are children of C. Siblings. All children which have common parent are collectively known as siblings. Thus, H, I, J are siblings of C. Likewise, B, C and D are siblings of root. If all siblings appear in definite order, say in alphabetical order, the tree is called ordered tree. The tree shown in this figure is in fact an ordered tree. Ancestors. Recall that in a tree structure, a node has a unique path to the root node. All nodes which appear on the path from a given node to the root node are called ancestors of the given node. For example, ancestor of M are F, B, and A. Descendant. A descendant is a child of a node or descendant of the child. All of the descendants of a node N are called a subtree rooted at N. In figure, the subtree rooted at B consists of nodes B, E, F, G, M, and N. A subtree may comprise a single leaf node. As we shall see later, the notion of subtree is of great help in partial processing of data contained in a subset of nodes. Level of tree. Obviously, the nodes of a tree are organized at different levels. By convention, the root node is at level 0. The children of root are at level 1. The children of root are at level 2, and so on. Notice that in figure the nodes B, C, and D are at level 1 and nodes E, F, G, H, I, J, K, and L are at level 2. The leaves M, N are at level 3. Height of a tree. The maximum level of a node in a tree is called height of a tree. Thus, the tree structure in figure has height 3. As we shall see later, the height of a tree plays a crucial role in determining the performance of search algorithms. A tree with the shorter height can be searched faster than an equivalent tree with greater height containing the same data elements. From the preceding discussion, we conclude that a tree data structure has two important characteristics which distinguish it from other data structures. First, unlike a stack and a queue, a tree is a non-linear structure. This implies that a data element in tree has more than one successor, which can be depicted in hierarchical fashion in two dimensions. Second, the defining property of a tree is the existence of a unique path from root to any of the tree nodes. This also implies that any node in the tree has a unique parent except the root node. If there is more than one path or more than one parent to a node, or there is no path, then the structure is not a valid tree data structure. It belongs to the data structure called graph. Figure shows an illustration in which node E has two parents, B and C. Also note that G has two paths to the root, namely G, E, B, A and G, E, C, A. Thus, we conclude that data structure is not a tree. Forest. We have seen that a node which has no path to the root of a tree is not considered part of the tree. This situation leads to the notion of a forest, which is defined as a set of disjoint tree structure. The disjoint property implies that there is no explicit path linking one tree to another. For example, if we remove the root node, we have a set of three disjoint trees shown in figure. Here, the forest is a set of three trees. Classification of trees. The tree structures are classified on the basis of maximum number of children permissible to be attached to a parent node. If in a tree a parent has 0, 1 to n children, it is called n-ary or n-way tree. A ternary tree, for example, is the one in which each node can have up to 3 children. If an n-ary tree contains nodes in specific order, the tree is called multi-way tree. In this case, each node contains a set of keys which determine range of values held by child nodes. For example, in a ternary tree, a node may contain keys A, H and T to imply that the first child would contain a character in the range A to G. Second child would contain character in range H to S, and third would contain characters in range T to Z. Multi-ways trees are frequently used in modern database management system to facilitate rapid searching of indexed records. In order to improve the performance of search operations, the height of tree is kept to be minimum by balancing the levels of subtrees. The resulting trees are often called as balanced trees. The term B-tree is often used to describe such trees. B+ tree is a variant of B-tree, in which all the leaves are linked by pointers to facilitate sequential searching, in addition to normal random searching. Indeed, B and B+ trees are cornerstones of all modern data file systems and database management system. Simpler versions of B-tree are used in some applications. Two such variants are known as 2-3 tree and 2-3-4 tree. The former contains 2 to 3 nodes per child and later 2 to 4 nodes per child. Figure shows a small 2-3 tree. A binary tree is the simplest form of tree data structure. In this structure, each node can have at most 2 child nodes. We shall study in great detail the binary tree structure in the subsequent section of the unit. For now, let us briefly look at some of the applications of binary trees. Application of trees. Many hierarchical data structures, analogues to trees, are commonly encountered in our daily life. A familiar example is the organization chart of a large department or company in which the hierarchy of the organization is shown. The root node shows the head or CEO. The children of root are usually the senior management, which are followed by middle or junior executives. The line or operation level staffs are generally exhibited at the leaf nodes. By systematically scanning the trees, from top to bottom, we can list all positions at different levels in the organization. Another common example of tree data structure is table of contents of a book or a document as shown in figure. The title of book is at the root. The book is generally organized into several chapters. Each chapter may be further organized into sections, and the sections may in turn be divided into subsections. Using one of the tree algorithms, we can print the table of contents of the book with chapters, sections, and subsections appropriately indented as shown. Perhaps the most common example of tree familiar to computer user is the structure of filing system in operating systems such as Unix, Windows, and Mac. Information and content of a set of files residing in the computer are organized in a hierarchy of directories and subdirectories as shown. The root of the tree represents the root directory. The data files are represented at leaf levels. By traversing tree, we can determine the contents of files in each subdirectories and print their size. Binary trees. We now turn to an important data structure called binary tree, which is the main focus of the present unit. Binary trees were introduced briefly earlier as an ordered tree structure in which each node can have at most 2 children. The first child is referred to as left child and second child as right child. Figure portrays an example of binary tree. Notice that binary tree is an ordered tree in which a distinction is made between left and right child nodes. Consider, for example, the 2 binary trees shown. Although both trees contain identical data elements, structurally these are treated as different trees. Full binary tree. A binary tree in which all nodes exist right up to the bottom level is called full binary tree. In other words, in full binary tree, no internal nodes are missing. Figure shows an example of full binary tree. Notice that in full binary tree, number of nodes at level 0, 1, 2, 3 are 1, 2, 4, and 8 respectively. We can use this observation to compute the total number of nodes in full trees of given height h. If n is the number of nodes, then by evaluating the sum, we have the formula, or after some simplification and taking logarithms of both sides, we can express the tree height in terms of number of nodes as, for example, the full tree in figure consists of 15 nodes. The height of tree is 3. Complete binary tree. A full binary tree represents an ideal situation. Such trees are rarely found in actual applications. Another structure which is close to a full binary tree is called complete binary tree. In a complete binary tree of height h, we have all nodes up to level h-1 exist. In other words, the tree is full up to level h-1. Some nodes may be missing at level h or at bottom level. All nodes at the bottom level must exist in leftmost positions. Figure shows an example of a complete tree. Notice that at the bottom level, some of the nodes are missing. The filled nodes at the bottom, namely I, J and K, are in the leftmost position. By way of contrast, this figure shows a non-complete tree because the available node at the bottom level are in the rightmost position rather than in the leftmost position. The distinction between a full tree, complete tree, and non-complete tree can be viewed more vividly by looking at the triangle arrow to the tree structure. Figure shows such triangles. The missing nodes are represented as unshaded area of the triangle. Types of binary trees. Binary trees are often classified on the basis of type of data structure contained in the nodes. Generally, 4 types of trees are used in different applications. These are characterized as ordered trees, expression trees, heaps, and decision trees. Ordered search trees. These are the most common trees which are widely used in several searching and sorting algorithms. The ordered tree is structured such that the data values in the left subtree are less than data values in the right subtrees. The data can be numbers, characters, strings, or key field. Figure shows an example of binary search tree. Notice that the value 50 contained in the root node is greater than all values contained in the left subtree, which contains 40, 30, 35, and 31. Also, root value is less than all the values in the right subtree comprising 70, 80, 65, and 75. This principle applies to all the nodes. We shall explore binary search tree in greater detail in a later section. Expression trees. Expression tree is structured to represent an arithmetic expression in a hierarchical manner. Each node contains either an arithmetic operator or an operand. For example, the expression a minus b and b minus a are represented as shown in figure. The expression for a complex arithmetic expression such as is shown in figure. Notice that operands in the expression tree always appear as leaf nodes and operators are contained in the internal nodes or in root node. In a later section, we shall examine how to construct an expression tree for an arithmetic expression. Heap. A heap is a special kind of binary tree which is structured such that the data value in each node is greater than the values contained in its left and right subtrees. Figure shows a heap. Notice that the value 80 in the root is greater than all values contained in the left and right subtrees. In general, this is true of all the subtrees rooted at different nodes. A heap can be used to represent a priority queue. Recall that in priority queue, the highest data value is always contained in the root. However, after removing the value held by the root node, the tree must be restructured to maintain the heap properties. Heaps are also used in sorting algorithms. Binary decision trees. A binary decision tree is structured to represent a sequence of if-then-else logical conditions and the resulting actions. Each node contains a test value or the appropriate action. Figure shows an example of a decision tree. In this representation, C1 through C6 are conditions and A1 through A7 are actions or conclusions. Decision trees are often used to represent a chain of rules for searching a knowledge base used in artificial intelligence or expert systems. They can also be used for parsing of logical expression in high-level programming languages. Implementation of binary trees. Implementation of a binary tree involves storage representation of nodes and coding of associated operations. We first consider the storage structure aspects of the implementation. Two common approaches are used to define tree structure. One method is known as linear representation or vector representation, which utilizes a one-dimensional array to store node values and pointers. The other method is known as link representation or pointer representation. It uses dynamic allocation of storage for tree nodes and associated pointers. We now examine these implementations. Linear representation of binary trees. In linear representation, we store node values and pointers in array cells. To implement the array-based structure, we first define a structure of node in C++ as we use a single array of C++ struct data type. Each struct cell contains data and pointers to child nodes. Then we create an array of nodes to represent the entire tree. We populate the tree by assigning node values and appropriate indexes. For example, the first node of a tree array would be collective values as shown. An implementation using single array is shown. The corresponding binary tree is also shown. Notice that left child and right child columns contain indexes of the corresponding left and right children in array. For example, for data C, the left child index is 6, which is the index for data D. Thus, D is the left child of C. If addition and deletion are made to the tree, the corresponding indexes would also change. In order to keep track of the root node and vacant cells, we would need to use two variables, say top and free, which point to the root cell and a list of vacant cells. We can also adopt a simpler approach to store elements of a tree in a single array of characters. It is based on a numbering scheme for the nodes of a binary tree. Figure shows a sample binary tree and its compact representation by an array of characters. The number next to a node represents the index value. The missing nodes are shown in the broken circle as shown. The nodes are numbered from top to bottom and left to right. Root is numbered 1. Its left and right children are numbered 2 and 3. The nodes at next level are numbered 4 through 7. In order to create an array for tree structure, we place node values in array cell according to the number assigned to the node. If a node is missing in the tree, the corresponding cell in the array is kept blank. The compact array representation is efficient if the tree is full or complete. Otherwise, a lot of space for missing nodes would be wasted. Consider, for example, a right-skewed binary tree in which all the nodes occur at the right children. Figure shows such a tree and the corresponding storage array. Notice that to store fewer elements of tree, we need an array of 15 cells. In this case, over 65% of the allocated space is wasted. Advantages and disadvantages of linear representation. We conclude that array provides a simple and efficient mechanism for representing binary trees. Given the location of a child, we can have direct access to the content of a node. Nonetheless, addition and deletion of node is rather inefficient because it would involve data movement within the array. Also, a lot of space is wasted if the binary tree is skewed or incomplete. This representation is useful if the number of missing nodes is small. Linked representation of binary trees. Linked list is the most common representation of binary tree. In this representation, the nodes have explicit pointers to the child nodes. Thus, each node contains the tree data element and addresses of the two children. Figure shows a linked representation of a simple binary tree. If a node is missing, the corresponding address value in the parent node is set to null, shown as / in the diagram. In linked representation, the storage space is allocated dynamically. The nodes are created as the need arises. The storage space is released when the node is deleted. For linked representation, we define two classes, one for the node and other for the tree structure and its associated methods. In C++, the class representing a node is defined as: it contains node data of character type. Left is pointer to left node. Right is pointer to right node. The structure of a class representing the tree would depend on the type of binary tree and its associated operations. Binary tree traversal. Traversing is the process of visiting the nodes of a tree in systematic way in order to process the data contained in the node. Each node should be visited exactly once. There are three standard ways of traversing, which are called pre-order traversal, in-order traversal, and post-order traversal. Pre-order traversal. The pre-order traversal is based on the following algorithm. Visit the root node first, traverse the left subtree in pre-order, traverse the right subtree in pre-order. Figure shows the traverse mechanism for a simple tree consisting of just 3 nodes. Root A is visited first. The left subtree B is visited next. The right subtree C is visited last. Thus, pre-order traversal is A, B, C. This figure shows the pre-order traversal of a bigger tree with 8 nodes. To traverse the tree in pre-order, we start at the root node A. Then traverse the 2 nodes B and D in the left subtree T1. Then we move to the right subtree T2, which contains a left subtree T3. Next, we first visit the root node C of right subtree. Then traverse the root node E of tree T3. This is followed by its visit to G and H. Last of all, we visit node F. Pre-order traversal of this tree is A, B, D, C, E, G, H, and F. In-order traversal. The algorithm for in-order traversal is: traverse the left subtree in order first, visit the root node, traverse the right subtree in order. Figure shows traversal of a simple 3-node tree. First, the left subtree B is visited. Next, root A is visited. Lastly, right subtree C is visited. Thus, nodes are visited in the order B, A, C. This figure depicts in-order traversal of a bigger tree. To traverse in order, First, the left subtree T1 is traversed to visit DB. Then, root node A is visited. Next, left subtree T3 within the right subtree T2 is visited. It consists of nodes G, E and H. Lastly, remaining nodes C and F of the right subtree are visited. Thus, in-order traversal leads to visit sequence DBA GEHCF. Post-order traversal. The algorithm for post-order traversal is: traverse the left subtree post-order first, traverse the right subtree post-order, visit the root node. Figure illustrate the traversal of a simple tree consisting of 3 nodes A, B and C. First, the left subtree B is visited. Next, the right subtree C is visited. Lastly, the root node A is visited. Thus, post-order traversal is BCA. Figure illustrates the post-order traversal of a bigger tree consisting of 8 nodes. In this case, first the left subtree T1 is traversed post-order. Then nodes D and B are visited. Next, right subtree T2 is traversed. It includes a subtree T3 consisting of nodes G, E and H. These nodes are visited in post-order G, E and H. Next, the remaining nodes of right subtree are visited, which include F and C. Last of all, root node A is visited. Thus, post-order traversal yields the sequence DBGHEFCA. Implementation of pre-order recursive traversal. We now examine the code to implement the recursive algorithm for pre-order traversal. A C++ interface for the tree is shown in figure. Each node would contain a single character. Further, it includes 2 methods, CRBT and BT. These are used to create the binary tree. It also contains pre-order method to traverse the tree in pre-order. The main operative methods for pre-order traversals are pre-order and pre. Pre-order function is called in main program. It passes the address of root node to the helper function pre, which implements the algorithm for pre-order traversal. Procedure is: invoke helper function, visit node and print data. Traverse left subtree pre-order. Traverse right subtree pre-order. The class methods are usually called from the function main in C++ program. The essential ingredients of main function are shown in figure. The detailed coding is shown in the demonstration that immediately follows. Implementation of in-order recursive traversal. You would recall that in in-order traversal, first the left subtree is traversed in order, then root is visited, and finally the right subtree is traversed in order. The necessary code for this algorithm is: invoke helper function, traverse left subtree in order, visit node and print data, traverse right subtree in order. Implementation of post-order recursive traversal. In post-order traversal, first the left subtree is traversed post-order, then the right subtree is traversed post-order, and finally the root node is visited. The code fragment to implement the algorithm is: invoke helper function, traverse left subtree post-order, traverse right subtree post-order, visit node and print data. stack-based implementation of pre-order traversal. The implementation of recursive procedure for traversal of binary tree is simple. However, in the recursive algorithm, the underlying procedural steps are not visible. An alternative approach is to use an iterative procedure, which is intuitively more clear. In iterative procedure, we would need to descend and ascend to different parts of the tree. The address value contained in each node enables us to descend to right or left subtree. The iterative procedure is essentially stack-based. The algorithm for pre-order traversal of a tree in iterative way is: Number 1. Push the address of root to stack and assign current node pointer P to the root. Repeat step 2 until P is not null. Number 2. Proceed down the leftmost subtree rooted at P. If there is any right node on the way, push its address onto the stack. Continue processing the nodes until the leaf node is reached and processed. Number 3. Pop the stack and assign the popped address to current pointer P. If P is null, exit. Otherwise, perform step 2. Let us consider an example of application of iterative procedure for pre-order traversal. This figure depicts a sample tree. Steps are summarized as: process A, push C, process B, D, pop C, push F, process E, push H, process G, pop H, pop F. Finally, the pre-order traversal is A, B, D, C, E, G, H, F. The code for iterative procedure for tree traversal is substantially more complex than the code for equivalent recursive procedure. In the former case, we have to deal with three classes representing tree node, stack, and tree structure. The interface for these classes are as shown. Here, B-tree class includes methods CRBT and BT to construct a binary tree. It contains stack preorder method to traverse the tree in stack-based preorder. Stack class utilizes an array of node objects to hold node data and pointer addresses. It contains push and pop method for storing and returning node data from stack. Code for the stack preorder method in the B-tree class is given in the demonstration. Stack-based implementation of in-order traversal. We can implement the iterative procedure for in-order traversal of a binary tree by using a stack. The algorithm based on the iterative procedure is: Number 1. Assign current pointer P to the root of the tree. Repeat step 2 through 3 until P is not null. Number 2. Proceed down the leftmost rooted at P, pushing onto the stack addresses of a node on the way. Number 3. Pop off the stack and process the pop node. If stack is empty, then exit. If the pop node has a right child, assign current pointer P to the right child and perform step 2. Let us explore how the algorithm can be applied to traverse a tree. Figure shows a sample tree. We follow these steps to traverse in order. Push ABD, pop DBA, push CEG, pop GE, push H, pop H, pop C, push F, pop F. Finally, the in-order traversal is DBAGEHCF. The implementation of the iterative procedure for in-order traversal uses the set of classes called node, stack, and tree structure, which we presented in previous section. For the in-order traversal, we use a method named stackInOrder. The code for this method is shown in demonstration. Stack-based implementation of post-order traversal. The iterative procedure for post-order traversal is more complicated than the pre-order and in-order procedure presented earlier. Here, we have to save addresses of a node and its associated child. After popping a node, the right child are handled differently. In order to make a distinction between left and right child, we use some special symbols, say $, which is saved with the address of the right child. The algorithm for post-order iterative procedure is: number 1. Assign a current pointer p to the root node. Then repeat step 2 to 3 until the stack is empty. Number 2. Traverse down the leftmost path of the tree root at p. At each node, push the address onto the stack. If there is right child, push it to the stack by flagging with $. Continue until the leaf node is reached. Number 3. Pop and process all nodes which do not have the flag $. If the stack is empty, exit. If a node with $, flag is popped, remove the flag and assign current pointer to the right child. Perform step 2. Let us see how this algorithm is used to traverse a tree in post-order. Consider the tree shown in figure. The necessary steps for traversal are summarized as: push A $C B D, pop DB, pop $C, push C $F, push E $H, push G, pop G, pop $H, pop HE, pop $F, push F, pop FCA. Finally, the post-order traversal is DBGHEFCA. In order to implement the post-order iterations, we need to modify the node class to include flag, which can be $, for a right child, and space otherwise. The new class structure is shown in figure. It is renamed as snode to make a distinction. The code for implementing the post-order procedure using a stack is shown in demonstration. Binary search trees. The binary search trees were briefly introduced earlier. Each node of a BST contains a distinct data item which identifies the contents of the node. The data item is commonly referred to as node key. In a search tree, the keys of all nodes in the left subtree are smaller than the keys of all nodes in the right subtree. In practice, nodes of a tree can contain simple data type such as numbers, characters, or strings. Figure shows some examples of binary trees containing numbers and characters. In many practical problems, such as databases, the nodes of a tree consist of records comprising several fields. One of the fields is designated as record key or key for the node storing the record. Figure depicts an example of search tree which stores personal records. In this example, personal identification number is the node key. Other fields are name and salary. We emphasize that a given set of data item can be arranged in a binary search tree in several ways. Figure shows how the set of characters A, B, C D, E, F, G can be represented in binary search tree with different tree structures. Notice that two of the structures are skewed to left or right. In these cases, the binary tree actually degenerates into a linked list. Later on, we shall see that the overall tree structure is determined by the order in which nodes are inserted into the tree. Operation on binary search trees. We can specify operations to create, manipulate, and visit nodes of a binary tree. The traversal methods considered in the previous sections are also applicable to binary search trees. In addition to the basic operations for a search tree, it includes create, destroy, and isEmpty methods. Inserting a node into binary search trees. In order to insert, we have to take two things into consideration. First, we need to find a location in the tree structure where a new node can be placed. To maintain the binary property of the tree, the new node must always be added as leaf node. Second, after insertion, we must ensure that binary search property is maintained. This implies that key of each node must remain greater than all keys in the left subtree and less than all keys in the right subtree. Example. Consider, for example, a binary search tree shown in figure. To insert a new node, say Q, we proceed as follows. Beginning with the root, we compare Q with the keys of a node. First of all, Q is compared to S. Since it is less than S, we move to the left child, which contains H. We compare Q and H. Since Q is greater than H, we descend to the right child, which is G. Again, Q is compared with G. Since it is greater than G and G have no children, we attach Q to G as its right child. Notice that after insertion of Q, the binary search property is preserved. Implementation of insertion procedure. A node can be inserted into a binary search tree by using an iterative or recursive procedure. The iterative procedure uses a loop to perform comparison of keys with the keys of left or right children until a leaf node is reached. If the keys are equal, the loop is terminated with some prompting message. In order to develop the code for insertion operation, we assume that each node of a binary tree stores a character string of some fixed size. The structure of node class is shown in figure. TNode class contains node data. It contains pointer to left child. It also contains pointer to right child. The complete code for iterative insertion procedure is given in reference notes. Searching a binary tree. Searching operation is performed to determine whether or not a node exists in a tree with the given key value. If search is successful, some kind of further operation is performed on the searched node, such as printing or updating the node contents. The algorithm for the search operation is similar to one for insertion operation. The search can be carried out interactively or recursive way. In either case, we start with root node. If the search key matches with the key of root node, the search process is terminated. Otherwise, we proceed to search the left or right subtree according to the key is less than or greater than the node key. If at any stage the key matches with the key of some node, the search process is terminated. If the leaf node is reached and no matches occur, the search process is terminated as being unsuccessful. Example. Consider, for example, a binary tree shown in figure. Suppose we want to know if a node with key values q exists in the tree. We start with the root node and compare q to key value s. Since q is less than s, we proceed to the left child, which has key n. Since q is greater than n, we move to the right child, which has key m. Since q is greater than m, we descend to the right child, which has the matching key. The search is finished. Next, suppose we look for a node with key k. The search path is shown in figure. In this case, the search is not successful because after traversing n, h and j, we end up with a leaf node whose key j does not match with the described key k. Sometimes we are interested in finding the largest and the smallest key stored in a tree. The search for these keys can be performed easily. To find the minimum key, we start with root node and proceed along the extreme left path until we reach the leaf node, which would contain the lowest key. Likewise, to find the maximum key, we proceed, beginning with root, along the rightmost path until we reach a leaf node, which would contain the maximum key. Implementation of search operation. As pointed out earlier, a binary search tree can be searched by using either iterative or recursive procedure. The iterative procedure is intuitively more clear because it reflects the searching steps as we descend the tree. A code fragment for search operation is given in reference notes. Performance of search operation. We have seen that in performing search on a binary tree, we descend from one level to next level. Further, at each level, we process exactly one node to match keys. In best case scenario, the search value would be found in the root node. In the worst case, the search process would be continued down to the bottom node. Thus, we conclude that maximum search time in worst case is proportional to the height of a binary tree. In our earlier discussion, we demonstrated that the height h of binary tree is given in terms of number n of tree nodes by the formula. Since runtime for search function is proportional to height, we can say that in big O notation, the time efficiency is O log n plus 1 minus 1. Recall that according to big O rules, the additive constant can be ignored in runtime expressions. We therefore conclude that in worst case, the performance of binary search tree operation is O log n. The binary search method is far more efficient than other search methods normally used with arrays or linked lists. For example, with an array containing 1 million unordered data items, we may have to perform on average 500,000 comparisons. If the same data is organized into a binary search tree, the number of comparisons would be around 20. However, for maximum performance, it must be ensured that in building a tree structure, the height of tree is kept to barest minimum. If, for some reasons, the trees become unbalanced and skewed to left or right, then it would degenerate into the linked list with height equal to the number of nodes. In this case, the performance of search operation would be O of n. Traversing binary search trees. The basic traversal operations, in-order, pre-order, and post-order, can be used to process the nodes of a binary search tree. However, we are particularly interested in the in-order traversal because it produces sorted list of node keys. Figure shows the in-order traversal path of a sample binary search tree and the result of traversal. Notice that the visited nodes have keys in ascending order. Performance of tree traversals. In traversing a tree, each node is visited exactly once. Thus, if there are n nodes in the tree, then traversal time would be proportional to n. In addition, some time it would be needed to process the contents of each node. As a result, total time of tree traversal and visit is proportional to n plus c, where c is a constant. We conclude that efficiency of tree traversal is O n plus c or On, ignoring constant c. Unit Overview. In this unit, we examine sorting and searching methods, which are commonly needed in a wide variety of computer applications. The unit begins with an introduction to sorting procedures. It also provides the background and formalism for implementation and analysis of sorting algorithms. The subsequent sections explore in detail the common sorting methods, their actual implementations, and performance analysis in terms of running time and memory space utilization. The unit also briefly reviews the techniques used for sorting the data stored on secondary storage devices. It concludes with an overview of searching methods applicable to arrays. The discussion is focused on the primary searching methods known as sequential searching and binary searching, and their comparative advantages and disadvantages. Objectives. After completing this unit, you should be able to understand the significance of sorting, distinguish between internal and external sorting, understand the logic behind the simple sorting methods of bubble sort, selection sort, and insertion sort. Comprehend the advanced sorting algorithms used in shell sort, quick sort, heap sort, merge sort, and radix sort. Distinguish between sequential and binary search methods. Compare the performance and relative advantages and disadvantages of fundamental search operations. Introduction to sorting. Sorting is a procedure for organizing a collection of data items in either ascending or descending order. The sequence of sorted data depends on the data type of element being sorted. The numeric data are always arranged according to their magnitude and sign. The character or string data are arranged according to the character set used on a particular computer. The collating sequence for characters can be ASCII, ABCDIC, or Unicode. ASCII is most commonly used. Unicode is useful for handling extended character sets in languages like Arabic, Urdu, and Chinese. Sorting is frequently applied to records in conventional files and databases. You would recall that in a database, each record consists of several data fields. Further, a record is uniquely identified by a key which may be composed of one or more fields. Records are normally sorted on a primary key. Sometimes we need to sort on a secondary key as well. For example, entries in a results sheet may be arranged by institutions and within institutions by grades. The associated data fields are referred to as sort keys. Benefits of sorting. Sorting is a fundamental and useful operation in several situations. First, sorting facilitates the task of searching a large data collection. It vastly improves the speed of searching. In time-critical applications, sorting precedes the searching operations. Sorting helps organize business information in a systematic and meaningful way. Invariably, a collection of business data is pre-sorted to generate reports, statements, and summaries. Sorting or indexing is a vital operation supported by Database Management System (DBMS). Much of the power of a database management system stems from the ability to provide rapid sorting on multiple data fields. Finally, sorting helps analyze large amount of scientific and statistical data. Sorting is also useful in recognizing patterns or identifying trends in time series. While sorting is useful, it is potentially the most time-consuming operation. As such, sorting algorithms have been a subject of intensive research ever since the emergence of computers. Over the past, several sorting techniques have been devised which range from simple but less efficient to most sophisticated and highly efficient. In this unit, we shall study commonly used and popular sorting methods which are known as bubble sort, insertion sort, shelf sort, quick sort, heap sort, merge sort, and radix sort. Types of sorting. The sorting algorithms are classified into two categories: internal sorting and external sorting. When sorting is done on a data collection which is kept entirely in the main memory, it is referred to as internal sorting. In most real-life applications, however, all data to be sorted cannot be accommodated in random access memory and is instead stored in secondary devices such as disk, diskette, or magnetic tape. In this case, blocks of data residing on auxiliary storage is loaded into the main memory, processed, merged with data on the devices. This mode of sorting is referred to as external sorting. The external sorting is slow compared to internal sorting because data blocks to be sorted have to be retrieved in a sequential order from the secondary device. By contrast, in internal sorting, any record can be directly accessed from the main memory. Framework for implementation of sorting methods. Before considering some specific sorting algorithms, it will be useful to devise a general framework for the implementation of various sorting methods. As before, we shall use a C++ interface class to specify the operations for creating an array, performing sorting on the array, and listing the contents of the array. The structure of interface sort class is as shown. Briefly, it performs these steps. The class is designed to handle array X of fixed size determined by the constant array size. Constructor initializes the variable count, which keeps track of the number of elements added to the array. Add method is meant to add a number to the array X. Display prints the contents of array. Sort A is the main sorting routine. It implements a specific sort algorithm such as bubble sort, heap sort, etc. We shall consider the detailed coding of sort A method in the relevant section. The codes for add and display methods will be given in program demonstration. Once the sort class is developed, it can be used in the C++ function main to invoke the sort procedures as shown. Analysis of sorting algorithm. The techniques for the analysis of general algorithm were presented in an earlier unit. You would recall that the performance or running time of an algorithm is expressed using big O notation. For example, an algorithm has O(n) efficiency if the running time increases in direct proportion to the size n of input data. Here, we examine the specific operations that influence the running time of a sorting algorithm. In general, sorting involves the following operations: accessing, fetching a data item from memory; comparing, making comparisons between a pair of data items; swapping, interchanging pair of data items; assigning, storing data item in a variable. In some cases, assignment can be a part of the swapping operation. The comparing and swapping are the most time-consuming operations and normally considered in the analysis. Based on the complexity, the sorting algorithms are classified as elementary and advanced. The elementary methods use iterative procedures consisting of nested loops. Consequently, their efficiency is determined by the number of loops to be executed. In general, the elementary sort methods have O(n)² or quadratic runtime. They are not efficient because the running time increases quadratically with the increase in the number of items to be sorted. As we shall explore later, the bubble sort, insertion sort, and selection sort have time efficiency O(n)² and are characterized as elementary sort methods. The advanced sort methods are based on recursive procedures. In this case, the data to be sorted is partitioned into smaller blocks which are recursively sorted. This approach is often referred to as divide and conquer. The advanced sorting methods have O(n) log n runtime. Since n log n grows at much lower rate than n², the advanced algorithms are much faster compared to elementary methods. The quicksort, merge sort, and heap sort belong to the category of advanced sorting algorithms. In some cases, the efficiency of an algorithm also depends on the existing order of the data to be sorted. For example, in some situations, the data might appear in pre-sorted order, sorted in reverse order, partially sorted, or randomly arranged. Thus, analysis of algorithms must also consider the worst case, best case, and average case scenarios. In general, a set of n data items can be arranged in n factorial ways. The possible arrangements grow tremendously as the number of items in the collection increases. For example, a collection of 10 data elements can have over 3.6 million arrangements. An acceptable algorithm should cater for all possible appearances of data. In average case analysis, it is assumed that all of the n factorial arrangements are equally likely to appear. The analysis of a sorting algorithm boils down to counting all exchanges and comparisons during the execution of iterative or recursive procedure. At each stage, the array or subarray is scanned from one end to the other. The process of complete traversing the array is often referred to as pass in sorting terminology. Bubble sort. Bubble sort is the simplest of all popular sorting methods and easy to implement. It works by comparing two adjacent data items and swaps them, if necessary, to bring them in proper order. Usually, the array is scanned several times. During the first pass, the first and second elements are compared. If found to be out of order, they are exchanged. Next, the second and third elements are examined and swapped if necessary. This process is repeated until the end of array is reached. As a result of the first pass, the largest element bubbles up at the end of the array. In the second pass, the subarray excluding the last element is processed. The passes are performed until the subarray is reduced to a single element. An example of bubble sorting is shown. In first pass, first two elements 56 and 89 are compared. Since these are in order, no exchange is required. Next, second and third element 89 and 77 are considered. Being out of order, these are swapped. Then, element in third and fourth position 89 and 10 are compared and swapped. Next element in fourth and fifth position 89 and 84 are considered and exchanged. This brings the largest element to the last position. In second pass, elements in first and fourth position are processed. In the third pass, elements in first and third position are considered. In the fourth pass, the array is sorted. Please click the button to watch bubble sort visualization. Implementation of bubble sort. Bubble sort is easy to implement. This figure lists the code for bubble sort method. Briefly, it performs these steps. We create two nested loops. Outer loop controls the passes. Inner loop iterates through the array to compare adjacent elements. Variable count is the total number of elements in the array X. This code fragment can be embedded into template class presented earlier to make a full-fledged program. Please click button to run interactive program for bubble sort. Analysis of bubble sort. We assume n is the size of array to be sorted. As discussed earlier, the bubble sort makes n-1 passes through the array in executing the outer loop. During pass 1, it makes at most n-1 comparisons. During pass 2, it makes at most n-2 comparisons and so on. Thus, in the worst case, it will make a total of n-1 plus n-2 plus n-3 up to +1 comparisons. The above series adds up to n-1 by 2 is equal n square by 2 minus n by 2. Thus, running time of bubble sort in worst case is O(n square by 2 minus n by 2. Ignoring the lower term and constants of the efficiency is O(n square. Note that worst case occurs when the array is sorted in the reverse order. In the best case situation, the array is already sorted. In the improved version, bubble sort makes only one pass and makes n-1 comparison. Since no exchanges take place, the sort is terminated. Thus, in the best case, runtime is O(n-1 or O(n). Thus, although bubble sort is simple to implement, it is not efficient for use on a large data set. Selection sort. Selection sort is one of the simplest sorting methods. To sort the array in ascending order, the array is searched for the largest element, which is then exchanged with the element in the last position. Next, the subarray, which excludes the last element, is searched again for the largest element. When found, it is exchanged with the next to last element in the subarray. This process is repeated until the subarray reduces to a single element. At this stage, the array will be sorted in ascending order. The same procedure can be followed to sort the array in descending order. An example of selection sort is shown in figure. The sample array consists of 5 elements. In the first pass, the largest element is found to be 68. It is exchanged with the element 23 in the last position. In the second pass, the subarray comprising first 4 elements is searched for the largest element, which is 62. It is exchanged with the last element 23 in the subarray. In the third pass, subarray consisting of first 3 elements is searched for the largest element. It is 23, which is exchanged with the last element 19. In fourth pass, the first 2 elements of the subarray are searched for the largest element. It is found to be 19, which is exchanged with the second element 10. The array is now sorted in ascending order. Please click the button to watch selection sort visualization. Implementation of selection sort. The selection sort method works in 2 phases. In the first phase, the array or subarray is searched for the largest element. To this end, a temporary variable is used which is initially set to the first element of the array. The array is then scanned by comparing each element with value held by the temporary variable. When a larger element is found, the temporary variable is reset to the largest element. At the end of the scan, the temporary element would hold the largest value in the array. In the second phase, the largest element is swapped with the last item. The process is repeated on the subarray. The code for selection sort is as shown. It uses variable xmax and imax to hold the largest value and index of the largest element. The variable count holds the number of elements in the array. It includes 2 nested loops. The outer loop performs passes over the array and subarrays. The inner loop iterates through the subarray to determine the largest value. Please click button to run interactive program for selection sort. Analysis of selection sort. As discussed earlier, the selection sort methods consist of 2 nested loops. If n is the size of input, the outer loop executes n-1 times. The inner loop executes n-1 times during the first pass, n-2 times during the second pass, and so on. Thus, the inner loop makes altogether n-1 plus n-2 plus n-3 plus up to 1 is equal to n-1 by 2 comparison over all the passes. At the end of each pass, the exchanges are made to find the largest value. Since the outer loop executes n-1 times, the total number of exchange will be. Thus, in the worst case, selection sort will perform comparison and exchanges. Thus, the total running time will be, or ignoring lower order terms and constant O(n) square. Since running time increases quadratically, the selection sort is inefficient for sorting large data sets. Observe that compared to bubble sort, the selection sort makes fewer data moves. More specifically, it makes roughly n square by 2 comparison and n exchanges. Thus, selection sort is a better choice compared to other quadratic sort methods when data movement is time-consuming operation. For example, in sorting of files with records but small sort keys, selection sort is preferable. Insertion sort. Insertion sort is a simple and intuitive sort method. As the name implies, it systematically picks array elements and inserts them into proper positions. The array is proportionally divided into two regions, one with sorted items and other with unsorted items. In each pass, an element is picked from the beginning of the unsorted region and moved into the sorted part. In order to do so, all elements larger than the element being moved are shifted one position to the right to make room for the picked element. Figure illustrates the insertion sort procedure on an array consisting of 5 elements. To begin with, the first element 83 is considered as belonging to one element sorted region. The second element is then moved and placed before 83. This insertion requires 83 to shift to the right. In fact, 83 occupies the position vacated by 22. Next, element 29 is considered. It would need to be inserted between the elements 22, 83 in the sorted region. Thus, element 83 is moved one place to the right to make room for the element 29. In the next pass element, 77 is considered. It would need to be inserted between the elements 29, 83. To do so, the element 83 is shifted to the right. Finally, element 67 is processed. It is placed between the elements 67, 83. The array is now in the sorted order. Please click the button to watch insertion sort visualization. Implementation of insertion sort. Insertion sort can be implemented in different ways. A simple procedure uses two arrays, one to store the source data and other for insertion of sorted elements. To save storage space, it is usual to use in-place sort, which uses a single array for sorted and unsorted items. In fact, the approach was followed in the insertion sort examples discussed previously. The source code for insertion sort procedures for in-place sorting is given in figure. It sorts an array of floating point numbers stored in array X of size count. The procedure is based on two nested loops. The outer loop controls the passes over the array. The inner loop iterates to perform comparisons and does the shifting by moving an element to the right. The variable temp holds the elements to be inserted into the sorted sub-array. Please click button to run interactive program for insertion sort. Analysis of insertion sort. The preceding discussion shows that insertion sort method utilizes two loops. If n is the array size, its outer loop makes n-1 passes over the array. For each pass, the inner loop makes one or more iterations to make comparisons and shift the data. In the worst case, when the inner loop is fully executed, it makes 1 plus 2 plus up to n-1 is equal to n-1 by 2 comparisons and equal number of shifting in each pass. The outer loop assigns an element to a temporary variable and then assigns the temporary variable to an array element. Since outer loop execute n-1 times, it causes 2 n-1 data moves. Thus, altogether, the insertion sort performs n-1 plus 2 n-1 is equal to n square plus n minus 2 operations involving comparisons, shiftings, and assignings. Thus, running time of insertion sort is O(n) square plus n minus 2 or O(n) square. More precise analysis would show that on the average, insertion sort makes about n square by 4 comparisons and n square by 8 exchanges. Thus, even though insertion sort has quadratic runtime, it performs better than bubble sort and selection sort. It is, however, inefficient for large data sets comprising several thousand data items. Shell sort. Shell sort, named after its inventor Donald Shell, is designed to improve the performance of quadratic sort algorithm. It is an extension of the insertion sort. In shell sort, comparisons are made between elements that are distant apart. The displacement is called increment. In each pass, the size of increment is reduced, so that in the last process, comparison is made between the adjacent elements. For this reason, a shell sort is sometimes referred to as diminishing increment sort. Thus, if initially the increment is taken as 4, comparison will be between first and fifth element, then between second and sixth, and then between third and seventh element, and so forth. In the next phase, the increment may be set to 3 or 1, but in the last pass, the increment must be 1 so that adjacent elements are compared. It is usual to refer to each pass as 4 sort, 3 sort, 2 sort, and 1 sort. An example of shell sort is shown in figure. The sample array consists of 8 elements. In order to apply shell sort method, we choose a sequence 4, 2, and 1 for the increment. Accordingly, the sort phase are named as 4 sort, 2 sort, and 1 sort. In 4 sort phase, an element is compared with another element with relative displacement of 4. Thus, elements 11, 75 are compared and exchanged. Next elements 72, 58 are compared and exchanged. Then elements 83, 12 are compared and exchanged. Lastly, elements 64, 83 are compared. Since these are already in order, no swaps are done. In the 2 sort phase, element displayed by 2 are compared. Thus, element in the first position is compared with element in the third position. This procedure is applied till the last element in the array. In the last phase, 1 sort, the elements in the adjacent positions are processed. Thus, elements 11, 50 are compared. Since they are already in order, no action is taken. Then elements 50, 12 are compared and swapped to bring them in ascending order. This process is continued across the array. At the end, the array is in sorted order. Please click the button to watch shell sort visualization. Implementation of shell sort. The implementation of shell sort method is similar to that of insertion sort. However, 2 modifications are required. First, an appropriate sequence set would need to be specified. Second, the inner loop should be modified to compare and shift elements which are located apart according to the specified increment sequence. We assume the sequence 4, 2, 1 for the increments. Starting with initial value 4, the increment would be reduced by half after the first cycle and set to 1 in the last cycle. Please click button to run interactive program for shell sort. Analysis of shell sort. Analysis of shell sort is considered a major improvement on quadratic sort algorithm. Although it can easily be implemented, the analysis of its performance is difficult and quite involved. It has been a subject of several investigations since it was introduced. Various analytical and empirical studies show that the performance of shell sort is largely influenced by the choice of increment set. The inventor of shell sort has proposed the sequence 1, 2, 4 up to n by 2 for an array of size n. It has, however, discovered later that the choice does not produce the best results. An alternative set 1, 3, 7, 15 was proposed by Hibbard. With his choice, it is shown that in the worst case, shell sort has running time O n 3 by 2. Sedgwick has shown that with the increments 1, 4, 13, 40, 121, in the worst case situation, the shell sort has O(n) 3 by 2 running time. In the average case scenario, the running time is O(n) 3 by 2. Thus, in either case, shell has significant improvement over bubble sort, selection sort and insertion sort, which have running time O(n) square. As such, shell sort is a method of choice for sorting of moderately large data sets consisting of few thousand data items. Quicksort. Quicksort was proposed in 1960 by C.A.R. Hoare. Unlike the previously studied methods which are based on iterative procedures, quicksort uses recursive algorithm. Broadly, a data set is partitioned into smaller subsets which are recursively processed. Thus, quicksort belongs to the category of divide and conquer procedures. Quicksort is among the fastest sorting methods and extensively used in a variety of situations. Because of its common use, several programming languages, notably C, C++, and Java, provide support for quicksort in standard libraries. The quicksort method works in two phases. First, the array is partitioned into two subarrays using one of the array elements as pivot, such that all elements to the left subarray are smaller than pivot and all elements in the right subarray are larger than the pivot. In the next step, the partitioning procedure is applied recursively to the left and right subarrays. In practice, several schemes exist to choose a pivot and partitioning of array into two subarrays. Later on, we shall see that the performance of quicksort is influenced to some degree by choice of pivot. Detail of procedure for performing this method is given in reference notes. Let us consider, for example, the array consisting of 10 elements. To apply quicksort, we follow the following steps. We select the leftmost element 60 as the pivot. The left and right pointers are set to point to the elements 60, 20, respectively. The array is scanned from right to left, beginning with element 20, skipping all elements that are greater than the pivot 60. Since 20 is smaller than pivot, we stop at the element 20. The element 20 is copied into the element pointed to by the left pointer, that is element 60. Next, the array is scanned from left to right, beginning with element 26, skipping all elements that are smaller than the pivot 60. The element 85 being larger than 60, we stop at element 85. The element 85 is copied to the element pointed to by the right pointer, that is, element 20. The array is next scanned from right to left, beginning with element 85 and skipping all elements that are larger than pivot 60. Thus, we stop at the element 13. The element 13 is copied into the element pointed to by the left pointer. Next, the array is scanned beginning with element 31 and skipping elements that are smaller than the pivot, and stopping when left and right pointers cross over. Now, both the pointers point at element 13 between the element 4, 87 as shown. We now replace the element 13 with pivot 60 and obtain. Observe that the element 20, 26, 13, 31 and the left of pivot 60 are smaller than the pivot, and the elements 87, 76, 73, 85 to the right of the pivot are larger than the pivot. We can apply the same procedure to the left and right partition until the array is sorted. Please click the button to watch Quick Sort visualization. Implementation of Quick Sort. The implementation of Quick Sort method consists of two parts: partitioning of array and recursive calls. For the partitioning, we shall follow the algorithm discussed previously. The implementation of recursive calls is simple and straightforward. Figure lists the complete code. It consists of two methods named QuickS and QSort. The function QuickS simply passes the upper and lower bounds of the array X to be sorted. The QSort is the main operative method for the quick sorting. It includes integer variables LB, RB and PA to hold the current values of lower and upper bounds and the index of the pivot. The variable pivot is assigned the leftmost element in the subarray. Code includes 3 while loops. The outermost loop tracks the left and right pointer and terminates when the pointer LL and RR cross over. The second inner loop scans the array from right to left. It decrements the pointer RR until an element lower than the pivot is encountered. The third while loop scans the array from left to right, incrementing the pointer LL until an element greater than the pivot is found. On termination of inner loops, the corresponding elements are swapped. When the outermost loop terminates, the value held by pivot is assigned to XLL. The last part of the code contains 2 recursive calls to process the left and right subarrays. Please click button to run interactive program for shell sort. Selection of quick sort pivot. Various studies show that choice of pivot has a significant impact on the performance of quick sort algorithm. As already discussed, the simplest choice can be either the first or the last element in the array. This is, however, not the best choice in all circumstances. For example, if the array is already sorted or partially sorted, the selection of the first element as pivot would greatly degrade the performance. To avoid such risks, several alternative methods have been proposed. 2 common approaches are called random selection and median of 3 selection. In random select, an element of the array is randomly picked and assigned to the pivot. Experience shows that this is the safest choice. However, in actual implementation, we need a random number generator to produce numbers between the upper and lower bound of an array or subarray. This is an additional overhead and increases the running time. Another method, known as median of 3, selects the middle element as the pivot. For example, if LL and RR are lower and upper bounds of array X, the index of a middle element should be MM is equal to LL plus RR by 2. Thus, X of MM is chosen as the pivot. Most popular implementations of quicksort method follow this approach. Empirical studies show that the median of 3 choice not only avoids the risk of degradation, it actually increases the performance by 5 to 10%. Analysis of quicksort. As we have seen in the implementation of quicksort, the significant operations are partitioning of array into smaller arrays, comparisons of elements with pivot, and swapping of element during scanning of the array. In order to determine the running time, we investigate the total amount of these operations. Let us first consider the number of partitions. We have seen that at recursive call, the array is split into 2 subarrays of nearly equal size. Thus, if we have an array of 7 elements, it will be split into 3 subarrays of sizes 1, 2, 4, because 1 plus 2 plus 4 is equal to 7. Generally, thus, we can say that an array of size n can be split into at most log n plus 1 partitions. After partitioning of an array, we perform n comparisons and n exchanges in worst case. Thus, the total number of major operations involved in quicksort are 2n log n plus 1. We therefore conclude that the running time of quicksort is O2n log n plus 1, or ignoring constants, O n log n. The logarithmic function n log n grows much slower compared to the quadratic function n square. Thus, quicksort is far too efficient compared to the quadratic sort methods named bubble sort, selection sort, insertion sort, and shell sort. However, as noted before, the performance of quicksort is also influenced by the existing order of input data. The worst case occurs when the array is already sorted. In this case, if the leftmost element is selected as to pivot, the array will split into 2 arrays of sizes 1 and n-1. Thus, altogether, 1 plus 2 plus up to n-1 is equal to n into n-1 by 2 comparisons and exchanges would be performed. As a result, the running time would be O n into n-1 by 2, or O(n) square. Thus, the quicksort would perform as poorly as any quadratic sort algorithm. Another major drawback of quicksort is that it is massively recursive. Recursion is generally performed by using computer's special memory known as heap. For problems involving a large number of recursions, enough memory may not be available on a particular machine. Further, some of the programming languages do not support recursion. Despite these drawbacks, quicksort is by far the fastest general-purpose algorithm. Heap sort. As the name implies, heap sort method uses a special data structure called heap to perform sorting. Heap is, in fact, a special kind of binary tree with 2 distinguishing features referred to as ordered property and completeness property. The order property implies that each node of a heap contains an element that is larger than both left and right children. It follows that in a heap, the largest element will always be located at the root. The completeness property means that all nodes of the tree up to the bottom level are filled. The bottom level is filled from left to right. An example of heap is shown in figure. Observe that each node contains an integer value which is larger than the values located in the child nodes. Further, the largest number 86 is located at the root of heap. The tree nodes are filled up to the third level. The bottom level has only two nodes with values 31 and 64, which are located in the leftmost positions. The heap sort method is based on the observation that in a heap the largest element always appears at the root level. Thus, heap sort algorithm consists of following steps. Map the array into a binary tree. Convert the binary tree into heap. Remove the topmost item at root level and place it at the end of the array. Move the element in rightmost bottom nodes to the root of tree. Repeat step 2 through 4 until the tree is empty. Quite obviously, the two main steps are mapping the array into a binary tree structure and converting the binary tree into heap. We first examine these steps in some detail. Mapping array to binary tree. Transforming an array into a tree structure is relatively simple matter. Using array elements, the binary tree is constructed in top to bottom and left to right order. Thus, the first element is placed at the root. The next two elements are placed as the left and right child nodes, and so on. Figure shows an example of an array and its corresponding binary tree. The number next to nodes indicate the tree order and corresponding indexes in the array. Converting tree into heap. In heap sorting, conversion of tree into a heap, commonly referred to as heaping, is a major task. Two common algorithms follow either top-down or bottom-up approach. In top-down procedure, the heaping process is started at the root level and proceeds down to the bottom level. In the bottom-up method, the reverse order is followed. We shall follow the top-down procedure in the subsequent discussion of heap sort. The heaping procedure will be as follows. Starting with first child of the root node, systematically consider all its elements up to the last leaf node. If an element is smaller than its parent, then swap the contents of pivot and child. If no exchange is required, move to the next node. Otherwise, continue repeating step 2 until the root is reached. Figure illustrates the heaping process. In the diagram, arrows show the movement of elements. Heaping process proceeds as follows. 31 and 58 are exchanged. Next, node 3 is examined. It contains element 60, which is larger than the element 58 at root node. So, 58 and 60 are exchanged. Then, node 4 is considered. It contains element 38, which is larger than the element 31 in the parent node. Thus, 31 and 38 are swapped. Next, node 5 is processed. It contains element 67, 38 and 67 are swapped. Node 2 now contains 67, which is larger than 60 in the parent root node. Thus, 67 and 60 are exchanged so that element 67 moves to the top. Then, node 6 is processed. It contains element 70, which is larger than the element 58 in the parent node. So, element 58 and 70 are exchanged. Next, node 7 is processed. It contains element 69, which is larger than the element 67 in the parent node. Therefore, the elements 69 and 67 are exchanged. Finally, node 8 is processed. It contains element 86, which is larger than the element 31 in the parent node. Therefore, 86 and 31 are swapped. Node 4 now contains 86, which is larger than 60 in the parent node. Therefore, 60 and 86 are swapped. The node 2 now contains 86, which is larger than 70 in the parent root node. Therefore, 86 and 70 are exchanged. Thus, elements 86 moves to the root. The tree is now fully heaped. Please click the button to watch visualization of heap sort procedure. Implementation of heap sort. The code for implementation of heap sort procedure is shown in figure. It contains two methods named hsort and crheap. The function hsort is called by the user program. It sets the size of array, then invokes the crheap heap creation method. The crheap converts the binary tree into a heap. The size of tree is passed as an argument to crheap. Click the button to run interactive program for heap sort. Analysis of heap sort. In heaping, an element is compared with its left child and swapped if child holds a larger element. It is then compared with the right child and swapped again if the right child holds a large element. In moving down an element, two comparisons and at most two exchanges are performed. We conclude that during reheaping, four major operations are performed at each level of the binary tree. In a preceding unit, we have seen that a binary tree of size n has at most log n levels. As such, the total number of comparisons and swap would be 4 log n. In general, the largest and smallest elements are swapped n times. This means that the total number of major operations involved in the reheaping is at most 4n log n. Therefore, the running time of the heap sort is O 4n log n or O n log n. Thus, heap sort has the same asymptotic behavior as the quicksort. Further analysis shows that heap sort is somewhat slower than quicksort. It is definitely faster than the quadratic sort algorithm. Heap sort has some advantages over the quicksort. First, unlike the quicksort, it is not recursive. Second, compared to quicksort, it is more robust. This means that the performance of heap sort does not depend on the state of input data. It is always guaranteed to be proportional to n log n, irrespective of the fact whether the input data is partially sorted or random. For such reasons, heap sort provides an ideal solution for sorting of data in real-time applications, because order of input data cannot be predicted in such situations. Merge sort. Merge sort is among the earliest of sorting techniques. It was used in electronic data processing applications for processing of data stored on magnetic tape files. In this method, we take two sorted subarrays and merge them to create a new array. To this end, the elements in the two subarrays are progressively compared. The smaller of the two is copied to the new array. This procedure is repeated until one of the subarrays is finished. The remaining elements of the other subarray are then copied to the new array. The merge-sort procedure can be recursive or iterative. In recursive method, the array is partitioned into two nearly equal subarrays which are recursively sorted. In the non-recursive procedures, the array is partitioned into a number of subarrays, each consisting of just one element. Each pair of one-element array is merged with the adjoint pair. Next, the merged array is partitioned to subarrays, each consisting of two elements. Then, two-element array is merged with the adjacent two-element array. Thereafter, array is partitioned into four-element subarray which are merged. This process is continued until no further partitioning is permissible. Figure illustrates the merge-sort procedure. The array consists of 10 unsorted elements. First, the array is split into one-element array, each containing the elements 90, 64, 10, 87, 46, 42, 37, 73, 8, and 71. Then, elements in the adjacent subarrays are compared. The first subarray contains 90, which is compared to 64 in the adjacent subarray. Since 64 is smaller, it is first copied to the auxiliary array and then element 90 is copied. Next, the pair of arrays containing 10 and 87 is considered. First, 10 is copied, which is followed by 87. This process is continued to the end. In the second phase, the auxiliary array is split into subarrays, each containing of two elements. Thus, the first array contains 64 and 90, and second contains 10 and 87, and so forth. The two elements array are then merged. In the third pass, the auxiliary array is again partitioned into subarrays, each contains 4 elements. The 4-element arrays are merged into an auxiliary array. Finally, an 8-element subarray is compared with remaining 2 elements, 8 and 71. The two subarrays are appropriately merged to produce an auxiliary sorted array. Click the button to watch visualization of merge-sort procedure. Implementation of merge-sort. The code for implementation of merge-sort method msort is listed in figure. It uses a variable ps which holds the partition size. It is initially set to 1 to partition the array into subarrays of 1 element each. At the end of a pass, the partition size is doubled. A while loop controls the partitioning process. It terminates the procedure when the partition size exceeds or equals array size. An auxiliary array, AX, is used to hold the merged subarrays. Variables J1, K1, J2, K2 are used to define the boundaries of the subarrays being merged. Variables J and K points to the elements of subarrays. A while loop checks that J remains less than or equal to J1 and K remains less than or equal to J2. a smaller of the elements in the subarray is picked and copied to the auxiliary array. The variable m determines the number of elements copied into the auxiliary array. After either of the subarray is exhausted, then remaining elements of this other subarray are copied to AX. After all the subarrays have been merged, the auxiliary array AX is copied back into the original array X. The process is repeated with a new pair of larger subarrays. Click the button to run interactive program for merge sort. Analysis of merge sort. In merge sort, at each pass the size of partition is doubled until it equals the size of array being sorted. Thus, the number of passes is equal to the number of partitions. While discussing quicksort, we saw that an array of size n can be split into log n partitions of sizes 1, 2, 4. Thus, the merge sort procedure of n data elements involves log n passes. During each pass, at most n comparisons are made. This means that altogether n log n operations are performed. In other words, the running time of merge sort is O n log n. Thus, merge sort has the same running time as quicksort and heap sort. Empirical studies show that merge sort is marginally faster than heap sort, but slower than quicksort. A major drawback of merge sort is that it requires extra storage space to hold the auxiliary array. Thus, space efficiency of merge sort is On. For very large data sets, the requisite space may not be available on a particular computer. Further, the process of data movement between the main and auxiliary array considerably slows down the sorting. Radix sort. Radix sort is an adaptation of an old procedure which was used to sort punch cards on a mechanical sorter. It was invented by H. Seward in 1954. Radix sort method can be used on a data collection when all data items lie in a small fixed range, such as decimal digits, characters, or binary digits. For each data item, we need a method to identify the bin to be allocated in each pass. The range R is often called radix. Thus, we have R is equal to 10 for decimals, R is equal to 26 for alphabets, and R is equal to 2 for bits. Click the button to watch visualization of radix sort procedure. Implementation of radix sort. The code fragment for implementation of radix sort is listed in this figure. It contains two classes, Q and radix. The constant iSize defines the maximum number. It also defines the total number of passes. The class Q includes three methods named insert, remove, and isEmpty. The class radix implements the sort method. It uses an array of queues named QUE to serve as bins for the sort method. In essence, P determines the integer value in x of j for the ith pass. Accordingly, x of j is moved to the QUE of P. Please click the button to run interactive program for radix sort. Analysis of radix sort. The major operation involved in the radix sort are extracting the digit or character positions, computing bin number, and merging data with the array. Suppose S is the maximum size of a data item and R the possible range or radix. R would equal 26, 10 or 2 for alphabets, integers and bits respectively. The radix sort will make S passes. In each pass, it would make at most R comparisons to allocate a bin. It would, for instance, check if a particular queue is empty. If n is the size of data input, altogether total number of S into R into n major operations would be performed. Thus, running time of radix sort is O S into R into n. S and R have fixed values. Thus, if the input data consists of short unsigned integer, the radix sort can have O(n) running time much faster than other sorting algorithms. In the worst case, when keys are very large, S may be the same order as n. Thus, radix sort will have O(n)² performance. A major drawback of radix sort is that it is space-wise not efficient. It requires large memory spaces to serve as bins. The performance of common sorting methods in terms of running time utilization is summarized in figure. As shown, the sorting algorithm fall into two major categories designated as quadratic and logarithmic. Obviously, logarithmic algorithms have much better efficiency. Bubble sort is simple and may be used for very small data sets. Selection sort can be used for small data sets with small keys and large record sizes. Insertion and shell sort give best performance among the quadratic algorithms. They can be used for moderately sized data sets. Among the logarithmic sort methods, quick sort gives best performance if the input data is randomly distributed. The heap sort is the best choice when distribution or order of input data is not predictable. It is a robust method with guaranteed logarithmic performance in all situations. Merge sort has somewhat better performance than heap sort. However, it requires memory space as large as the array to be sorted. For a very large dataset, it may not be a good choice. The radix sort shows good performance if the dataset has short integer keys. We conclude that choice of sorting method is dictated by the size of keys, size of dataset, and pre-existing order of the input data. Another consideration is the amount of available storage space for auxiliary arrays or queues. Sorting. As mentioned earlier, external sorting refers to sorting of data residing on secondary storage devices such as tapes, disks, and diskettes. In this case, the major time-consuming operations include reading from and writing to the external storage. To sort a large data file, records are read in blocks and loaded into the main memory. Each block is sorted internally using a suitable method and is written back to the secondary device as a sub-file. The smaller sets of files are then merged into a single sorted file. The merging of sub-files is essentially based on the same technique as used in internal merge procedures. Since movement of large records is a time-consuming and costly operation, in practice, relevant sort keys are stored in a separate file with pointers to record in the main file. This file is referred to as index file. The index file is sorted by the relevant key. The sort file together with the record pointer can be used to list records in the main file. In general, it is possible to create indexes on several fields. Figure shows an example of index file used with the personal file. File 1 is the main file. File 2 is index file for ID. It is sorted by ID number and contains pointers to the record in file 1. File 3, sorted on name, is the second index file. It also holds pointers to the personal file. Suppose we want to access the main file via index file, file 2, using pointer. We can list the records in the main file in order of ID. Again, using pointer in file 3, we can access the main file and list records sorted by names. The indexing has following advantages. The size of the file used in external sorting is tremendously reduced. Arrangements of records in the main file is not disturbed. Thus, not only the time in data movement is saved, the chances of corrupting the files are eliminated. If the records in the file are added, deleted, or updated, the index file is updated more efficiently compared to sorting of whole file. Searching. Searching is the process of locating an item in a data collection. It is an important activity in several computer applications. In fact, a large amount of time of millions of computers in Internet is spent in searching a large variety of databases. The searching techniques differ with size and complexity of data structure. We have already studied the method for searching binary trees. Two advanced search methods known as breadth-first search and depth-first search are used for locating a specific item in a complex data structure. It is commonly used on trees and graphs. We shall explain these techniques later. For now, we explore two simple methods normally used to search arrays. These are categorized as linear search and binary search. Binary search. A binary search can be performed if the array is in sorted order. In this method, an element to be searched is compared with the middle element of the array. If the middle element is greater, the search is continued to the first half of the array. On the other hand, if the middle element is smaller, the first half of the left is ignored and search is performed on the second half. This process is continued until either a match is found or the search area shrinks to zero size. Note that at each step, the array to be searched is reduced by half. Figure illustrates the binary search method. The element 28 to be searched is first compared with the middle element. The index of middle element is 0 plus 12 by 2 is equal to 6. Thus, 28 is compared with 45. Since 45 is larger than 28, the search is now restricted to elements 0 through 5. The index of the middle element in the subarray is 0 plus 5 by 2 is equal to 2. The new middle element is 12. Since 12 is smaller than 28, it is next confined to element 3 through 5. The middle element of this subarray is 28, which matches with the element being searched for. Linear search. Linear search or sequential search is used for searching arrays in which data items are not in a specific order. In this method, beginning with first item, each item is successively compared with the item to be searched for. This process is continued until either a match occurs or the array is exhausted. The process of searching of an array is illustrated in figure. Click the button to watch visualization of linear search procedure. Implementation of linear search method. The implementation of a linear search method is quite simple. Figure shows a listing of code fragment. It is designed to search an array X of integer for a value held by the variable key. The array is scanned in a loop. If a match occurs, the index of the matching element is returned. If the loop terminates without a success, -1 is returned. Please click the button to run interactive program for linear search. Analysis of linear search. To search an array of size n, almost n comparisons are made between array elements and items to be searched if the element happens to be non-existent or if it is the last element. Thus, in a worst case, the running time of linear search is O(n). The average number of comparisons would be n by 2. In the best case scenario, the elements being searched for is the very first item. Thus, in the best case, the efficiency of linear search is O(1). Linear search is not an efficient search method, but if the array consists of randomly distributed elements, choice is restricted to linear search. Implementation of binary search method. An implementation of binary search method is shown in figure. Code includes a search method named bsearch. It is meant to search an array X of size count. It received an argument key of type integer to be searched for in the array. A loop is set up to scan the array. At each iteration, it computes the index of the middle element using variable left and right, which identify the left and right boundaries of the sub-array. The key is compared with the middle element. If middle element is larger than key, variable right is set to middle, where middle is the current index of the sub-array being scanned. If middle element is smaller, left is set to middle plus 1. This process is continued until key matches with the middle element and value held by middle is returned. Otherwise, -1 is returned, which signals that search has failed. Please click the button to run interactive program for binary search. Analysis of binary search method. We have seen that in the binary search method, at each step, the size of array to be searched is reduced by half, and a comparison is then made with the middle element. Thus, the number of comparisons is equal to the total number of partitions of sizes 1, 2, 4, and so on. If n is the total number of elements in the array, then, as discussed earlier, the total number of comparisons would be log n. Thus, binary search method has running time O log n. The logarithmic function grows much slower as compared to a linear function. A comparison of the two functions is shown in figure. The binary search method is more efficient as compared to the linear search method. For example, in order to search an array consisting of 1 million items, we would need to make around 20 comparisons. A linear search of the array of the same size would involve about 50,000 comparisons on the average. A major limitation of the binary search method is that the array should be pre-sorted. This step itself would be time-consuming for a large array. For very small data set, however, there will not be much difference in the linear and binary search methods. Further, the binary search method is not applicable to other data structures in which the middle element cannot be directly accessed. For example, it cannot be used on a linked list because there is no simple way to identify and access a middle element. Unit Overview. In this unit, we study an important data structure called graph. A graph is a versatile and flexible structure. It can be used to represent complex relationship among the elements of a data collection. The relationship can be nonlinear and of different types, such as one-to-many, many-to-one, or many-to-many. Because of these characteristics, graphs are often used for modeling and simulation applications, not only in computer science, but also in other disciplines. The unit begins with an introduction to graph terminology and an overview of graph applications. It then discusses various ways of representing graph and associated operations for manipulating graph data. In particular, the graph traversal methods known as depth-first search and breadth-first search are explored together with their implementations. The unit concludes with the description of important graph algorithms attributed to Dijkstra, Prim, and Kruskal, which are commonly used in graph applications. Objectives. After completing this unit, you should be able to describe basic terminologies and concepts about graph data structure, learn about common graph applications, understand the main operations associated with graph data structure, understand the implementation of graph methods for matrix representation, represent a graph using adjacency matrix, learn about the significance of path matrix and different algorithms for computing path matrix. Describe the algorithm for determining shortest path matrix. Understand linked list representation of a graph. Describe the depth-first and breadth-first search methods and their implementations. Understand Dijkstra algorithm for finding minimum traversal cost for a graph. Use Kruskal's and Prim's algorithms for finding minimum spanning trees. Learn about topological sorting. Introduction to graphs. Graph is a data structure that has been a subject of intensive study over the past several hundred years. Famous mathematician Euler is credited with doing pioneering work on graph theory. Using a graph representation, he was able to solve the celebrated problem of crossing 7 bridges to the island of Königsberg without using any one of the path more than once. However, many of the important and useful graph algorithms have been discovered over the past 4 decades, almost in parallel with the advent of computers. Unlike other data structures, graphs are often studied as mathematical constructs. As such, much of the terminology and notions associated with graph data structures are borrowed from the discipline of discrete mathematics. In this section, we examine the relevant definitions and concepts. Graph. A graph is a collection of data items called vertices and edges. Vertex stores some kind of data. An edge represents a connection between pairs of vertices. A vertex is sometimes referred to as node or point. An edge is also termed as arc. Suppose A and B represent a pair of vertices in a graph. The edge connecting A to B can be represented as AB, or more commonly as enclosed in a pair of parentheses. In formal theory of graphs, set notation is often used to represent a graph and its associated elements. Thus, a graph G is defined as a set VE where V is a set of vertices and E is a set of edges. If V1, V2, V3 up to Vn are the vertices, then using set notations we can write. More often, graphs are shown pictorially using diagrams. Typically, a rectangle, oval, or circle represents a vertex. Lines or arcs are used to depict the edges. Suppose, for example, a graph consists of vertices A, B, C, D, and E with edges AB, AC, BC, CD, CE, DE. Figure shows a diagrammatical representation of this graph. It is emphasized that in pictorial representation, the location of vertex is immaterial for some applications. Thus, vertices can be laid out in several ways. For example, this figure is an alternative representation with a different geometrical configuration of the same set of vertices and edges. Although these two pictorial representations give different looks, they represent the same set of data elements in the graph. Graphs are classified on basis of properties of the edges and their orientation. The major categories are undirected, directed, weighted, and multigraph. We now briefly overview the salient features of each type. Undirected graph. In an undirected graph, the edges are not assigned any direction. Thus, there can be at most one edge between a pair of vertices. The undirected graph is used to represent one-to-one relationship among the data elements. Figure shows an example in which all elements are linked together. It can be shown that an undirected graph with n vertices can have at most n into n-1 by 2 edges. The edges of an undirected graph are denoted by unordered pair of vertices enclosed in parentheses. For example, an edge connecting vertices V and U is represented as UV. Note that UV and VU represent the same edge. An undirected graph is also termed as undigraph. A graph in which all the edges are present is called complete graph. By contrast, a graph with comparatively fewer edges is called sparse. Generally, a graph with less than n log n edges, where n is the number of vertices, is categorized as sparse. Directed graph. In a directed graph, each node is assigned a direction. The edges of a directed graph are usually denoted by an ordered pair of vertices enclosed in angle brackets. Thus, the pair UV represents an edge which starts at vertex U and ends at vertex V. The first vertex is referred to initial vertex and the second as terminal vertex. As such, UV and VU represent different edges connecting the same pair of vertices. A directed graph is also termed as digraph or network. Figure shows an example of a directed graph. It consists of vertices A, B, C, D, and E, and edges AB, BA, AD, ED, CB, DC, and ED. Weighted graphs. In weighted graph, the edges are assigned data values referred to as weights. Weighted graphs have several real-life applications. A weighted graph might, for instance, represent cost of transportation between two locations, amount of data traffic between workstation in a network, or distances between two cities. Figure shows an example of a weighted graph. The numbers attached to the edges are the weights. A weighted graph can be directed or undirected depending on the nature of application. For example, a weighted directed graph can represent flight journey between two airports because flight distances between two airports might be different depending on the flight paths for forward and backward journeys. Multigraph. A multigraph is a generalization of a directed graph. In their structure, there can be multiple edges between a pair of vertices. Such edges are termed as parallel edges. Figure shows a multigraph. Observe that there are three edges between the vertices A and B. There are two parallel edges from A to B and one edge from B to A. A multigraph is used to represent a many-to-many relationship among graph elements. Graph paths. A path between a pair of vertices is a sequence of vertices in the graph which are connected by successive edges. We can denote the path by enclosing the list of vertices in a pair of angle brackets. For example, in figure, ABDE represents a path between the vertex A and E. The length of a path is the number of edges that occur along the path. For example, the length of path ABDE is 3. The vertices which have path of length of 1 are called adjacent vertices or neighbors. For example, in this figure, vertices B, C and D are neighbors of vertex A. A vertex is said to be reachable from another vertex if there exists a path between the vertices. In the figure, vertex B is reachable from vertex A or vertex E, but A is not reachable from any other vertex. Loops and cycles. Two special paths termed as loop and cycle are important in graph applications. A loop is an edge that begins and terminates at the same vertex. Figure shows an example in which vertex A and C have loops. A cycle is a path that originates and terminates at the same vertex, but unlike a loop, a cycle includes more than one vertex. Figure shows a graph with a cycle represented by the path ADCA. Another cycle is ABA. In an undirected graph, the path between a pair of vertices cannot be called a cycle because backward and forward traversals are along the same path. In an undirected graph, a cycle must involve at least 3 vertices as shown in figure. A graph that does not contain any cycle is called acyclic. Simple path. A graph path in which all vertices and edges are distinct is called simple path. In a simple path, repeated vertices or edges are not permitted. Sometimes a distinction is made between simple path and elementary path. In an elementary path, repeated vertices are permitted along the path. Figure presents simple and non-simple paths in a graph. The path A, E, B, C, E, D from A to D is non-simple because vertex E is repeated along the path. On the other hand, path AED is simple. Graph connectedness. A graph is said to be connected if there exists a path between all pairs of vertices. In other words, each vertex is reachable from any other. Connectedness in an undirected graph is simple because the edges can be traversed in either direction to reach a vertex. Figure shows a connected undirected graph. Observe that there is no direct connection between the vertices B and C. However, C can be reached from B via vertex A. Connectedness may involve paths of length greater than 1. In a directed graph, connectedness is more complex. For example, a vertex A may be connected to B, but B may not be connected to A. A graph is called weakly connected if one or more vertices are not reachable from any other vertex. Figure shows an example of weakly connected graph. Observe that vertex A is not reachable from any other vertex. A graph is termed unilaterally connected if at least one of the vertices in a pair is reachable from the other. Figure shows a unilaterally connected graph. For example, A is not reachable from B, but B is reachable from A. Likewise, B is not reachable from C, but C is reachable from B via D. A graph is called strongly connected if, for all pairs of vertices, both vertices are reachable from either of the vertex. In other words, if A and B are any arbitrary vertices, then A must be reachable from B and B must be reachable from A. Figure shows an example of a strongly connected graph. Consider, for example, the pair of vertices A and D. Observe that A is reachable from D via C and D is reachable from A via B. You can verify that every vertex is reachable from any other vertex. Degree of vertex. The number of edges that connect a given vertex to other vertices is called degree of the vertex. In a directed graph, the number of edges that originate from a vertex is called out degree. Likewise, the number of edges that terminate on vertex is called in degree of the vertex. The in and out degrees of the vertex V are denoted by the expression. Consider, for example, the graph shown in this figure. It can be verified that in degree of A is 2 and out degree of A is 4. The in degree of E is 2 and out degree of E is 0. Application of graphs. As noted before, a distinguishing feature of a graph data structure is its ability to represent complex relationship among data elements. In general, a graph can be used to represent a structure in which many-to-many type relationship exists among the data elements. In real life, we come across many such examples. Some familiar examples are computer networks, electrical circuits, transport networks, assembly lines, molecular structures, and databases. In computer networks, workstations and servers can be viewed as vertices and links between the devices as edges. Thus, a graph may be used to configure a network for optimum performance. For example, using appropriate algorithm, we can determine the shortest or most economical routes for dispatching packets of information along different paths in a network. Electronical circuits are another common example of application of graphs. Connectivity and performance of a circuit can be ascertained with the help of graph theoretical methods. Graphs are also useful to schedule various tasks in an assembly line of an industrial plant when certain tasks must be completed before the next task is started. The most familiar examples of graphs applications are found in transport industry. For example, airport, cities, and other sites can be represented as vertices, and the air routes, railway lines and roads as edges. A graph can be used to answer such questions as: is there a connection between two given locations? If so, what is the minimum cost of transportation? Or what is the shortest route? In plain words, one may want to know a travel schedule with minimum travel time or minimum fare between any pair of cities. Several graph algorithms exist to solve such problems. Graphs are also useful in studying molecular structures. The graph-theoretic methods can be used to differentiate between structures with different configuration of a set of molecules. Finally, in a database application, graphs are frequently used to represent various types of entity relationships, often referred to as ERD diagram. Operation on graphs. As with other data structures, we can perform several operations on graphs to access the data elements and update the information contained in the graph. We can also modify the relationship among data elements. Some useful common operations include the following: inserting a new vertex into the graph, removing an existing vertex, inserting a new edge between a given pair of vertices, removing an existing edge, determining degree of a vertex, determining reachability of a vertex, finding paths of different lengths between a given pair of vertices, determining the shortest path between a pair of designated vertices, traversing a graph. We shall examine the implementation of these methods while studying different ways of representing graphs. Matrix representation of graph. We have seen that a graph can be represented diagrammatically with direction of edges shown explicitly. However, pictorial representation is not useful for analytical studies of a graph. Further, the pictorial representation is not feasible when a graph contains a large number of vertices and edges. There are alternative ways of representing graphs. Two common methods are known as matrix representation and list representation. The choice depends on whether the graph is dense or sparse. We first look at the matrix representation. In matrix representation, the edges between the vertices are represented as elements of a matrix called adjacency matrix. The rows and columns of the matrix are labeled by graph vertices. If an edge between a pair of vertices exists, then corresponding row and column contains 1 and 0 otherwise. We can algebraically define an adjacency matrix by using matrix notation. If Aij is an element of a matrix A in ith row and jth column, then Aij equal 1 if there exists an edge between ith and jth vertex, Aij equals 0 otherwise. Consider the graph shown in figure. It is a directed graph with vertices labeled A, B, C, D, E, F. This figure shows the matrix corresponding to this graph. Since in some programming languages such as C, C++, integers 0 and 1 refer to logical false and true values, the adjacency matrix is sometimes referred to as Boolean matrix or bit matrix. An adjacency matrix that contains the weight associated with edges of a weight graph is called weight matrix. A major advantage of matrix representation is that we can determine the degree of vertex easily by simply summing the entries in the corresponding rows and columns of the adjacency matrix. For example, Consider the vertex D. The sum of values in the row corresponding to the vertex is 2. We conclude that our degree of D is 2. Also, the sum of entries in the column corresponding to D is 3. So, the end degree of D is 3. By looking at the pictorial representation in figure, you can verify that 2 edges originate from D and 3 edges terminate at D. Another advantage of the adjacency matrix is that insertion and deletion of edges can be accomplished easily. In order to remove an edge, we simply toggle the value 1 to 0 in the corresponding row and column. The biggest advantage of matrix representation is that we can compute path length by performing basic matrix operations. We shall look at this aspect later. A drawback of matrix representation is that insertion and deletion of new vertices involves complex procedures. To insert a new vertex, we would need to add a new column and a new row. Also, the columns and rows would need to be shifted to place the new vertex in proper location. In order to delete a vertex, we remove the corresponding row and column from the adjacency matrix. However, after removal of matrix elements, we would need to shift the succeeding rows and columns to update the adjacency matrix. This is a time-consuming operation, particularly if column or row to be deleted happens to be towards the end. Another drawback of adjacency matrix is that it results in uneconomical utilization of storage space when the number of edges is small compared to the number of vertices. In such a case, the adjacency matrix would contain a large number of zeros and would be sparse. Consider, for example, a graph consisting of 10 vertices with 4 edges. The adjacency matrix would contain 100 entries with only 4 ones. Thus, 96% storage space would be wasted. This drawback is overcome in a list representation of a graph. Click here to watch visualization of adjacency matrix. Array-based implementation of graph. We have seen that a matrix is analogous to a two-dimensional array. We can therefore use the two-dimensional array to store the elements of an adjacency matrix. We also use a one-dimensional array to store information contained in vertices. Therefore, in order to implement graph's data structure, we define a class which consists of 2 arrays and includes associated graph operation. We call this class graph matrix. The structure of the class is shown in figure. It consists of following arrays: two-dimensional array E to store edges, one-dimensional character array V to store vertices. The basic operations are implemented using the following methods: add vertex to insert a new vertex, add edge to insert a new edge, del edge to delete an existing edge, display to print the graph. It is assumed that vertices store single characters. The edges are represented by n into n matrix. The actual codes for the class methods are given in the demonstration. Click button to run the array-based implementation of a graph. Path length in a graph. The adjacency matrix shows whether or not a path exists between a pair of vertices. In other words, it tabulates all paths of length 1 in a graph. In some applications, we are interested to know whether there are paths of length greater than 1 between a pair of vertices. Consider, for example, a simple graph shown in this figure. Note that vertices A and B are connected to vertex C, but it is not directly connected to B. Therefore, although there is no path of length 1 between A and B, there is also another path of length 2, because B is reachable from A via C. Using adjacency matrix, we can find paths of different lengths for a graph. It can be shown that square of the adjacency matrix gives paths of length 2. If A is an adjacency matrix with element Aij in ith row and jth column, then the element Bij of the A square are given by the following formula for the matrix multiplication, where sigma denotes sum obtained by varying k from 1 to n. Here n is the number of vertices. The formula is based on the preceding observation that if a path exists between the ith and kth vertex, and there is path between kth and jth vertex, then there is a path of length 2 between ith and jth vertex. Consider, for example, the directed graph shown in figure and associated adjacency matrix A. Next figure shows the square of A. From the matrix A square shown in the figure, we can conclude that there is one path of length 2 between A and C. This is, in fact, the path ADC. Also, there are two paths of length 2 between D and E. These are DAE and DCE, shown with bold arcs. It can be shown that if A is the adjacency matrix, then in general A raised to the power n represents the number of paths of length n between different pairs of vertices of a graph. For example, a cube would tabulate the number of paths of length 3. The elements of the cube of adjacent matrix A are given by the formula, where Pij refers to an element in the ith row and jth column of matrix A cube. In other words, Pij is the total number of paths of length 3 between the ith and jth vertex of a graph. This figure shows the graph matrix A raised to power 3. The matrix indicates that these paths are CDAE and CDDE. The first is a simple path since no vertex is repeated along path. The other is non-simple because vertex C is repeated. Click here to watch computations of path lengths. Path matrix. A path matrix for a graph shows whether or not a vertex is reachable from a given vertex, irrespective of the path length. In other words, a vertex A would be reachable from B if there exists a path of any length. A path matrix is a special matrix that tells if there is a path between a pair of vertices of a graph. We can define a path matrix P by the relations Pij equal 1 if there exists a path between the ith and jth vertex, equal 0 otherwise. If the ith vertex is reachable from the jth vertex, then there must be at least one path of length 1 or of length 2 or length 3 and so on up to n, where n is the number of vertices in a graph. Therefore, we can determine the reachability of all vertices by summing powers of adjacent matrix A as follows, where n is the total number of vertices. The path matrix P can be determined by setting all non-zero elements in M to 1. figure summarizes the computations of different powers of the adjacent matrix for a sample graph. By setting non-zero entries to 1, we obtain the path matrix. Observe that second vertex is not reachable from any other vertex. The last vertex is reachable from any other vertex. A graph is said to be strongly connected if for any pair of vertices A and B there is a path from A to B and there is also a path from B to A. The graph is said to be weakly connected if there is a path from A to B or there is a path from B to A. This means that for a strongly connected graph, the path matrix does not contain any zeros. The path matrix shown in the preceding example is weakly connected because there are several zeros in the matrix. Warshall's algorithm for path matrix. The computation of powers of the adjacency matrix is a laborious and time-consuming process. Warshall proposed an alternative method which is more efficient. In this formulation, the elements of the adjacency matrix are treated as logical values. The path matrix is computed using the following recursive formula. Pij denotes an element in the ith row and jth column of the path matrix. The operators OR and AND are the logical operators. Figure lists the code for the Warshall's algorithm. It is assumed that the path matrix initially contains logical values which correspond to the entries in the adjacency matrix. Remember, character ampersand and bar represent Boolean operations and OR respectively in C++. Shortest path matrix. In graph application, sometimes we are interested in finding the shortest path between a pair of vertices. The Warshall's algorithm gives information about the existence or absence of a path between any pair of vertices. An extension of Warshall's algorithm can be used to determine the shortest path between any two vertices. The shortest path algorithm uses a recursive relation by finding minimum distance between a sequence of vertices. In essence, it computes the sum of weights Wik and Wkj and compares these with the weight Wij. If Wik plus Wkj is found to be smaller than Wij, it is used in the next step of computation. In order to ensure that zero entries in the adjacency matrix are not considered as minimum values in a computational step, all zero values are initially set to a very large value, which is referred to as infinity. The code fragment for computation of shortest path is listed in figure. A temporary array Q is used to store results of computations. First, the non-zero elements of the weight matrix W are copied into Q. Then, the zero values are set to 32,000, which represent infinity for the purpose of computation. It is assumed that graph is directed and that weights are non-negative values. N represents the number of vertices in the graph. Click here to watch the computation of shortest path matrix for the sample graph. The graph can be generated interactively. Linked list representation of matrix. We have seen that matrix representation has the drawback that insertion and deletion operations on a graph are not efficient. Further, matrix representation would be wasteful from storage viewpoint if a matrix is sparse. Strictly speaking, we say that a graph is sparse if it contains fewer than n log n edges, where n is the number of vertices. An alternative representation that uses linked list is more efficient for the sparse graph. In the linked list representation, there are different ways of showing relationship among the graph elements. A common approach is to use a linked list for a set of vertices which are adjacent or neighbors of a given vertex. Thus, in general, if there are n vertices, the list representation would consist of n linked lists, one for each vertex. Further, in order to provide access to each list, each vertex must be accessible by a head pointer. The set of linked lists is referred to as adjacency list. Consider, for example, the graph shown in figure. A cross in the link part of a node represents a terminal node of a list. The order of edges in a list can be different. For example, in the first linked list vertex, D can also precede vertex C. The operations of insertion and deletion of edges can be easily performed on the linked list representation. A new edge can be added by inserting tail node in the relevant linked list. An edge can be deleted by removing a node from the list. However, insertion or deletion of vertices is quite complex. In order to remove a vertex, we would not only need to delete the entire linked list corresponding to the vertex being deleted, but also remove all the edges in other lists which are linked to the vertex. This would involve scanning of all the linked lists to find if there is an edge to be deleted. List-based implementation of graph. In order to implement a graph using a list approach, we define two classes called vertex and graph list. The class vertex specifies the structure of a vertex. The specification for the class graph list is shown in figure. It is composed of an array of pointer v, which stores head pointers for each of the linked lists, and it includes the following methods. Add vertex to insert a new vertex to the graph. Del edge to remove an edge from the graph. Add edge to insert a new edge between a pair of given vertices. Get vertex to return the index number of vertex. Display to print the graph. Click here to run interactive demonstration for list-based implementation of a graph. Traversing graphs. In traversing a graph, we visit every vertex to extract information contained in vertices and edges. It is ensured that each vertex is visited only once and that no vertex is left out. There are two standard methods for traversing a graph. These are referred to as depth first search and breadth first search. As with trees, we can use recursive or iterative procedure for traversing a graph. The iterative procedure uses auxiliary data structure such as stack and queue to store vertex data as the graph is traversed. The saved information is then popped and processed in appropriate sequence. Sometimes we use special terminology to identify the processing step. A vertex which is to be pushed to a stack or queue is said to be in ready state. When the vertex is placed in the stack or queue, it is said to be in wait state. Finally, when the vertex is popped off, it is said to be in the processed state. Obviously, all visited vertices are in the processed state. We now examine the algorithms for the depth first search and breadth first search. Depth first search. In depth first search, we start with some arbitrary vertex, say x, and process it. Then, we push all neighbors of x, say x1, x2, x3 onto the stack. We pop the stack to process x1 and push all neighbors of x1, say x11, x12, x13 onto the stack. This procedure is continued until all vertices are processed. The vertices that are processed are marked as visited. The algorithm for depth-first search consists of following steps. Step 1. Initialize all vertices and mark it as unvisited. Step 2. Select an arbitrary vertex, push it onto the stack. Step 3. Repeat step 4 and 5 until stack is empty. Implementation of depth-first search algorithm. In order to implement the depth-first search algorithm, we define a class which includes the graph traversal algorithm together with the methods for creating and displaying a sample graph. Figure shows the structure of the class named GraphList. It uses two external classes called vertex and stack. The graph itself is implemented as a linked list. Observe that the class includes following private members: a pointer array vertex of size max, which holds pointers to the graph vertices; an array vi of logical values which shows whether or not a vertex is visited; a stack sk, which is used to handle vertices in wait state. The class methods are as follows. Add vertex inserts a new vertex into the graph. Add edge creates a new edge between a given pair of vertices. Disp prints a linked list representation of graph. DFS implements the depth-first search algorithm. Push ADJ handles vertices which are in wait state. GetIndex is an auxiliary function to obtain index of a given vertex. Click the button to run the interactive program for the implementation of depth-first search algorithm. Breadth-first search. In the depth-first search algorithm, we first descend down the graph and then scan vertices sideways. In the breadth-first search, this order is reversed. We first traverse the vertices widthwise and then depthwise. As before, we select an arbitrary vertex, say x, of the graph. We process x. Next, we process all neighbors of x, say x1, x2, x3. Also, we push the neighbors of x1, say x11, x12, x13 onto a queue. Next, an element is removed from the queue and processed, and all of its neighbors are processed. This process is continued until all vertices have been processed. Observe that in breadth-first search, we use a queue rather than a stack. Recall that adding an element to a queue is called enqueuing, and removing an element is called dequeuing. The algorithm for breadth-first is as follows. Step 1. Initialize all vertex to mark them as unvisited. Step 2. Select an arbitrary vertex, add it to queue. Step 3. Repeat steps 4 to 5 until queue is empty. Step 4. Remove an element from the queue. Process the element and mark it as visited. Step 5. Insert all neighbors of the processed element into the queue. Step 6. Check if any vertex is left unvisited. If so, repeat step 2 using an unvisited vertex, otherwise exit. Consider the graph shown in figure. It shows the breadth-first traversal path in broken arcs. The numbers refer to the order in which the graph is traversed. Figure tabulates the steps involved in traversing the graph. Observe that the order in which the vertices are enqueued is arbitrary. We can push the vertices beginning from left to right or from right to left. Sometimes the vertices are sorted in ascending order before being pushed onto the queue. Naturally, each of these procedures would yield a different traversal path. Briefly, the steps are as follows. A is enqueued and dequeued. A's neighbors D, C, B are enqueued. B is dequeued and processed. B's only neighbor E is enqueued. C is dequeued and processed. C's neighbors F and G are enqueued. D is dequeued and processed. D's neighbor H is enqueued. E, F, G and H are successively dequeued and processed. Click the button to watch the visualization of BFS algorithm. Implementation of breadth first search algorithm. In order to implement the breadth first search algorithm, we define an interface class named GraphList. The specification and structure of the class is as shown. It uses two external classes called vertex and queue. Vertex defines the structure of graph vertex. The class queue is used to hold temporarily the vertices which are in wait state. The main class consists of the following methods. Add vertex inserts a new vertex into the graph. Add edge adds a new edge between a given pair of vertices of the graph. Disp shows adjacency list of the graph. BFS performs the breadth first search. NQADJ is an auxiliary function that performs NQ and DQ operations in traversing the graph. GetVertex returns the index number of a vertex. Click the button to run an interactive program for breadth first search algorithm. Spanning trees. A spanning tree for an undirected graph is a subgraph which includes all the vertices but contains no cycles. A graph can have several spanning trees. Figure shows a sample graph and some of the associated spanning trees. Observe that all trees contain the same number of vertices as in the original graph. Further, all trees have same number of edges. It can be shown that a graph with n vertices has n raised to power n minus 2 spanning trees. We can create spanning trees in several different ways. One simple method is to remove all edges that form cycles. When the number of vertices is very large, this approach may not be feasible. We can use graph traversal algorithms to generate various kinds of trees. We can create spanning trees by using depth first search algorithm. During the traversal, we can mark edges associated with the visited vertices. After the search is completed, the marked edges will form a spanning tree. This tree is sometimes referred to a depth first search spanning tree. Likewise, we can create a breadth first search spanning tree. Minimum spanning trees. Spanning trees can also be built for undirected weighted graphs. As before, there can be a large number of weighted spanning trees. However, there is at least one tree with the least possible summation of all edges. This tree is said to be minimum spanning tree. The minimum spanning trees are useful in many real-life applications of graphs. Telephone network provides a good example. The network can be configured using a minimum spanning tree so that all receivers are linked together with minimum length of cable. Another example could be linking of a group of islands connected with bridges so that total bridge span is minimum. The minimum spanning trees can also be used to determine air routes between a number of cities so that all cities are linked together with least travel time or lowest travel cost. In order to determine the least cost or shortest path for a graph, two important algorithms have been proposed. These are named after their inventors and called Kruskals algorithm and Prim's algorithm. Both provide efficient methodology but differ in their approach. Kruskals algorithm. The Kruskals algorithm was discovered in 1956. In this algorithm, the edges of an undirected weighted graph are scanned one by one. At each step, an edge with the least weight is picked and added to the corresponding vertices of a graph. If an edge creates a cycle, it is dropped. The algorithm can be implemented by pursuing the following steps. Step 1. Remove all edges from graph. Step 2. Arrange edges in ascending order of the weights. Step 3. Pick the smallest edge and add it to graph. If the new edge creates a cycle, reject it. Step 4. Repeat step 3 until all vertices have been processed. The resulting subgraph, which may contain fewer edges, would be a minimum spanning tree. Consider, for example, the undirected graph shown in figure. The edges and the weight are tabulated in next figure. The action column shows whether an edge is added or dropped. This figure shows the minimum spanning tree built by using the Kruskals algorithm. The thick lines represent the tree. The total path length of the tree is 10 plus 23 plus 30 plus 40 equal 103. Note that edges BD, AC, CE have been rejected because they form cycles when joined with other pre-selected edges. The edge BD, for example, is dropped because it produces a cycle with edges AB and AD, which are already selected to be the part of spanning tree. Kruskals algorithm is classified as a greedy algorithm because it immediately selects an edge with the lowest weight. It is an efficient algorithm for building minimum spanning trees. It can be shown that for a graph with n vertices and m edges, the running time of Kruskals algorithm is O(m log n). Click the button to watch a visualization of Kruskals algorithm and to print a tray. Prim's algorithm. Prim's algorithm is an alternative method for creating minimum spanning tree. As the name implies, the algorithm was proposed by Robert Prim in 1957. Unlike the Kruskals algorithm, which makes selection of edges, the Prim's algorithm picks vertices. Briefly, the algorithm proceeds as follows. Step 1. Select an arbitrary vertex. Mark it as visited. Step 2. Repeat steps 3 to 4 until all the nodes have been examined. Step 3. Find an unvisited vertex which is connected to any of the visited vertices and has the smallest weight. Step 4. If the edges do not form a cycle, add it to the tree and mark the selected vertex as visited. If the graph is not connected, then the algorithm would produce a spanning tree for the connected components of the graph. Consider, for example, the weighted graph shown in figure. We use Prim's algorithm to create the minimum spanning tree. The result of examining different vertices is shown in figure. The vertex A is selected as the initial vertex to be added to the tree. Figure shows the minimum spanning tree for the graph. The edges of the trees are shown in thick lines. If n is the number of vertices and m the number of edges, the Prim's algorithm has running time of O m plus n log n. Being a logarithmic, it is quite efficient. Dicastra's algorithm. We have already studied that a path matrix can be used to find the shortest distance between any pair of vertices in a directed weighted graph. The algorithm, however, does not provide the details of the shortest path between a given set of vertices. Dicastra's proposed an algorithm which generates a trace of the shortest path. The algorithm has many useful applications. For example, it can be applied to find the shortest driving distance between cities connected by roads. Dicastra's algorithm works like the Prim's algorithm. It begins by selecting an arbitrary vertex and proceeds outward to cover all vertices. Unlike the Prim's algorithm, however, Dicastra's algorithm repeatedly computes the distance between a source vertex and the vertex being examined and selects the sequence of edges which yields the smallest summation. This process is continued until all the vertices have been examined. By storing the information about the vertices and edges selected, it is possible to create the shortest path between any vertices. The implementation details of the Dicastra's algorithm can vary depending on how the information pertaining to the vertices and edges is stored and updated at each step. Click the button to watch the working of Dicastra's algorithm. The visualization also creates a trace of all steps involved and generates the shortest path between a selected pair of vertices. Topological sorting. We have seen that vertices of a graph can be listed in several ways by using different traversal methods. A special arrangement of vertices of a directed graph without cycle is termed as topological order. In this arrangement, if an edge is directed from a vertex A to vertex B and an edge is directed from B to C, the list ABC is termed as topologically sorted list. Essentially, every successive vertex must follow a predecessor vertex in the sort order. In general, there can be several sort orders. For example, if there is a directed edge to C from both A and B, then the topological order can be with ABC or BAC. Topological sorting has several applications. For example, in certain course offering, some courses may be prerequisites for other courses. A sort order would list the order in which the courses can be taken. Another example of topological order is the scheduling of tasks that must be completed before others can be started, such as in an assembly line. There are several algorithms for performing topological sorting. In one simple method, a vertex which has no successor vertex is chosen. It is added to list, and all edges that end at this vertex are deleted. This process is repeated on a next vertex that has no successor, until all the vertices have been added to the list. The result is a sequence of vertices which would be in topological sorted order. Consider, for example, the directed graph shown in the figure. Note that it does not contain any cycle. We can apply the preceding algorithm to generate a topologically sorted list of the vertices. Since E has no successor vertices, we select E and add it to the list. Also, we delete the edges that terminate at E. At this stage, the list contains only E. Next, we choose D, which has no successor, and add it to the list. The edge terminating at D is deleted. Now the list contains vertices D and E. Now the vertex C has no successor, so we choose C and add to the list, which now consists of vertices C, D, E. Since edges from B and A to C are deleted, we can select B and A and add them to the list. In this way, we end up with the list BACDE, which is the desired topological sort order. Figure diagrammatically shows sequence of vertices with broken line. The edges of the original sample graph are also pictured.